Hello, can you hear me? Thank you very much for the nice introduction. Well, the Bézier Award gives me a wonderful opportunity to talk about my own work, so I'm very pleased. Well, I think there are five major areas where I contributed to geometric modeling. Integration of solid modeling and parametric surfaces, reverse engineering geometric models, multiple surface fitting with local and global constraints, multi-sided surface representations, and then survey papers. So let me start with the first area, integrating parametric surfaces into solid modeling. Let's go back to the early 80s. You will not believe this. There were two separate disciplines. There were two separate groups of people, and they hardly talked to each other. So it was obvious that these two paradigms must be united. And at that time, there were fundamental questions. Maybe today these are all trivial, but at that time, we asked how to merge half space based implicit surface geometries with bonded parametric surfaces, what sort of general interrogation techniques are needed, how to compute robustly surface-surface intersections, how to compute edge blends, and how to generate vertex blend. Now, in this arena, I picked one topic, and that is setback vertex blending. Let's state the basic problem. Given n edge blends fillets meeting at a given vertex, and we want to compute a surface patch that smoothly connects the edge blends and the surrounding primary surfaces. And there are general requirements like we want to handle vertices with arbitrary valency. We want to permit arbitrary blending radii. We want to fair shape. We want to resolve special cases such as tangential and cusp-weight edges. And also, we prefer that the final patch must be independent on the edge blending sequence. Now, the traditional algorithm is the following. You take the rail curves of the blends, the boundaries of the blends, and you compute pairwise intersection points. Let me see whether I can move this. Yes. So here are the intersection points. Then you connect the intersection points by profile curves, and then you get an n-sided patch. Now, there are limitations. This fails in many cases and does not satisfy the general requirements. And there are typical problems like skewed isolines, overhanging patches, and you have to fiddle with lots of special cases. So we say no and try to use the new setback-based algorithms. So we terminate the edge blends at profile curves But these profile curves are shifted backwards, moved away from the vertex, and we insert spring curves. Now, spring curves run on the primary surfaces. So in this way, we get a two-sided patch. So this is the message. Vertex blending should be treated as a two-sided patch, and all the rest are special cases of this two-sided patch. For example, when the spring curves degenerate into a single point. Now, the key benefits, all requirements are satisfied, intermediate cases can be handled, and the shape of the vertex blend will not depend on the edge blending sequence. Few pictures. Traditional method, isoparameter lines are skewed, setbacks produce a natural transition. Other example, take this cube, small radii on the top, large radii for the horizontal. Traditional method, uneven radii may produce overhanging patches, like here. That's not good. Setbacks produce a natural transition, like here. Let me show you a few pictures of setback type vertex bending, six-sided patch, eight-sided patch, 10-sided patch, and also uh, an interesting example where you have tangential edges and you have cuspoid edges. And the setback solution can produce an appropriate smooth transition. So that was vertex blending. And let's move on to the second area, reverse engineering. Well, an alternative term is digital shape reconstruction. By definition, reverse engineering is the art of converting 3D measured data into valid and consistent 3D geometric model. Again, go back to history. In the early 90s, commercial 3D scanners and graphic computers became more powerful and more affordable. And this boosted the CAGD community, leading to the very first reverse engineering review paper written by myself, Raoul Martin, and Jordan Cock. And this happened to be a milestone paper. The citation index is more than 2,000. And apparently it had a good impact. The reverse engineering pipeline was elaborated, uh, the basic problems, the basic difficulties were identified, and this paper opened avenues for future research. So let me talk a little about the pipeline, how we get from point clouds through triangular meshes, through regions, through surfaces, to full BREP models. It's better if I show you a few pictures. So phase one is just 3D scanning the measurement. Phase two, you may have multiple point clouds that you want to register and merge. Then you have to generate a triangular mesh. You decimate the mesh, you enhance the mesh, you repair the mesh. And then comes the most difficult part of reverse engineering, and that is segmentation. So you have a large triangular mesh, and you want to partition that large mesh. You want to generate distinct regions and a separator set. So here you can see the distinct regions, and the red is the separator set. And what you want is that the region structure should correspond to the face structure of the CAD model. And if you take the separator set, the feature skeleton will correspond to the graph of the edge structure. If this segmentation is correct, then your CAD model will also be correct. So this is the most crucial phase of reverse engineering. Now, once you have segmentation, you can classify these regions. And there is a well-defined hierarchy of surfaces. So you start with simple planes, then you try to discover extruded surfaces, then rotational surfaces, then surfaces defined by profile curves, and at the end, what remains, those will be represented by freeform surfaces. Phase six. So once you have the region structure, once you have the classification, you can fit primary surfaces by the surface type. It's always a special least square fitting that depends on the actual surface type. And for freeform surfaces, we need to create a good parameterization for the unknown to be fitted surface. And I will talk about this in a minute. Phase seven, constraint fitting for groups of surfaces. I will talk about that as well. And once you have the primary surfaces in phase 8, you fit secondary surfaces that smoothly connect to the primary surfaces. Then you generate edge blend and vertex blend. Finally, quality assurance, and at the end, you build a BREP model and you can export this geometry to CAD/CAM systems. Okay, so the next main topic is labeled fitting. You want to fit a freeform surface. Your input is a trimmed region classified as freeform. So this is partial information. You have only part of the geometry, the region data, but you want to fit a full surface, a full four-sided tensor product B-spline. And here we have basic requirements. We need a smooth surface with a natural control grid. And we want the surface to extend beyond the region without even curvature, with even curvature distribution. And this is, again, crucial. Look at this segmented mesh. If you have a surface with wiggling, then you will get a wiggling intersection curve at the end. If you have a smooth surface, yeah, you will get a smooth intersection curve. If you have a wiggling surface, you will get a wiggling blending surface. If you have a smooth surface, though, you will get a proper blend. Now, surface fitting, many of you know this basic problem that there are weak control points. So there are control points that are not fully determined by the underlying data. And that may produce wiggling. That means that the control points after least square fitting can float in the 3D space. So this will give you ugly surfaces. However, if you apply our method with labeled fitting and parametric extension, then you will get nice surfaces. So the challenge, fit a smooth quadrilateral patch with a good parametrization. Well, clearly, many parameterizations exist, but you want to pick a good one. The clue, align the trimmed boundaries of the region and the sides of the target surface. So try to find an optimal orientation by labeling. Here you can see the labels of the B-spline surface, and you want to assign these labels partially to the sides of the region. A label setting can be automatic or can be manual. Let me show you how it works. So here we have the same region, and then we show different labeling. And different labeling will produce different parameterizations in the domain space. So here, example, we assign these two and these two, then we assign this and this. So clearly, you will get different surfaces. Now, there are two basic steps. Number one is the flattening. Here we apply constrained parameterization. We have the labeling information. So in the plane, we can get a consistent mesh in a way that the side triangles are constrained to the labels. So this is what you get with this constraint Arab. And then you can add artificial supplementary triangles. So at the end, you will have a full rectangle of triangles, adding the artificial ones. And then you can go back to 3D space. And once you have it, the weak control point problem has gone. So you have a full mesh now, and you can fit a full surface. And you will understand. You will better understand this with this workflow figure. Here you can see the labeling, various segments. Then you can create a so-called guiding frame. The guiding frame will tell you how the to-be fitted surface will be positioned in the 3D space. Then you go to the domain, you flatten. Then you do extension in the domain space. So there are artificial triangles. Then you go back to 3D and create this nice 3D mesh, and then you can fit. So that's the basic idea. A labeled fitting will keep the geometry the right location position. A few examples. Here is our input. Without labeling, you will get this domain and you will get this surface. If you do labeling, then it will constrain the surface and you get a much better surface quality. Another example, this is your input. Without labeling, you would get this one and this surface. With labeling, you add the artificial triangles, and then you will get this surface geometry. So that was labeling, and let's move on constraint fitting. Constraint fitting also a very critical phase in reverse engineering. Well, think about it. You have noisy data, you have various numerical algorithms like registration, triangulation, repair, segmentation. So all these are numerical algorithms. Now, if you fit individually, that will yield inaccurate engineering models. Now, this is not acceptable for a real CAD/CAM application. So the challenge is how to build perfect models ready to be integrated into CAD/CAM systems. So, for example, you have a plane, you have a cylinder, the angle between the normal and the axis is 88. You don't want that. You want 90. You want to recognize that you are within a certain tolerance and you want to enforce that the normal of the plane to be fitted will be parallel to the axis of the cylinder. So we want to reproduce the design intent. We want to discover and enforce engineering constraints such as perpendicularity, parallelism, tangency, concentricity, rounded values, and symmetry, and we want to fit in a tricky manner. So we said that segmentation yields disjoint regions, classification assigns surface type to each region, and you can perform local fitting. So you take the local point cloud, you compute the unknown parameters of the surface by minimizing. So the unknown parameters can be the radius and the axis of the cylinder, or it can be the control points of a freeform surface or anything. Depends on the surface type. Now you can set the constraints by automatically, by some threshold, or interactively, and you will get nonlinear algebraic equations to couple the surface geometries. So for example, in the previous example, you will couple the parameter of the plane, normal, and the axis parameter of the cylinder. And then you merge all parameters and you get a system of a large nonlinear, you get a large nonlinear system where you fit simultaneously. So you have a groups of surfaces fitted together while the constant equations are satisfied. And this leads to a large nonlinear system that fortunately you can solve. If interested, you can read it in this paper. And we've managed to solve basic problems here that are difficult problems, how to generate so-called auxiliary elements, how to compute proper distances, faithful distances, how to perform this whole in an efficient manner, and how to handle overdetermined or underdetermined determined systems. Let me show you a simple example, 2D example. Here you have three segmented circular arcs. Here you can see the input, one segment, second segment, third segment, and you want a smooth connection. That is, you want common endpoints, and you want a tangential connection, and you want that the radii should be multiple of 10. If you do constraint fitting, then you can solve the system. Here you can see the independent fit, and here you can see the constraint fit. As you can see, the radii are okay now. These constraints, the tangential and the multiple constraints, are satisfied. And here you can see that the average deviation is somewhat larger than the original. But we understand this. You have to loosen the constraints in order to satisfy the constraints. I remark that there are also global constraints. You can detect partial symmetry planes, or You can detect a global dimensioning grid. That's also very, very useful in many cases. Or you can compute local or global coordinate systems. Also, we've managed to extend our work not only for the conventional geometry, but also for freeform geometry. So the constraint fitting for freeform curves and freeform curve surfaces can be done. And here you can see a few examples. Initial fitting suggests two surfaces should be perpendicular along their curve on intersection. We can introduce an auxiliary curve with point normal sequences, and we can incorporate these point normals into the large system application. And then we fit these two freeform surfaces according to these constraints. Another example, here you want smooth connection between freeform surface and the cylindrical surface, and then again you can fit accordingly. The third example, that you do initial fitting and recognize that there is a smooth connection here, and here there must be a perpendicular constraint since this is a symmetric part. So that means that the left and the right must connect smoothly. And here you can see the result of the two surfaces and the isoform. Okay, so that was reverse engineering, and let me move on to multi-sided surface representation. Well, this is a Bezier talk, so I'm supposed to talk about generalized Bezier constructions, and I will talk about three generalized Bezier schemes. Well, you know that general topology surfacing is a classical problem in CAGD, and modeling exclusively with four-sided patches that can be cumbersome, computationally difficult. In many cases, it's almost uh, it is impossible. So there is a strong demand for patchwork with multi-sided surfaces, and we know a rich variety of surfacing schemes. That this really also started in the early 80s. Think of Malcolm's work or Gregory patches or Luke de Rose, Hosaka Kimura, and many others. I would say that the two main applications are curve network-based design and then hole filling with vertex blending. And here you can see a few examples. Now, the basic problem. So what is the basic problem? We want to create a natural surface transition that smoothly interpolates boundaries and cross derivatives. So this is our most fundamental question. Well, here you can see some curves. Oh, here. Then you may have normal fences along the boundaries. Then you may be able to generate good ribbons, and then you will get the multi-sided patch. So this is what we want. There are the constraints, and then you want a smooth uh, transition. Here you can see the mean curvature map. Here you can see the isoform. And I say that it would be hard to model this simple shape using trimmed surfaces, control polyhedra, or quad patches. Recently, we've published a survey paper uh, on parametric surface patches. In this talk, we are not interested in trim surfaces or composite quad surfaces. We are interested in genuine n-sided patches, which means that there is a single surface equation that can define our entire surface. And we concluded that basically there are two groups of approaches. The first is the blend of surface intervals. So this is the Kunstpatch-like thinking. So you just define the interpolant surfaces and blend together. The second one is the control point based patches where you weigh the blending functions. The control points will be multiplied by blending functions. It's not the interpolant surfaces, just the control points. And there are generalized Bezier patches and there are generalized B-spline patches. Okay, so ribbon-based modeling. So what are the basic issues here? How to define ribbons that are compatible with the quadrilateral tensor product Bezier and B-spline patches. How to create an appropriate domain. Appropriate may mean polygonal or curved or multi-connected. How to parameterize quadrilateral ribbons over a multi-sided domain, including open and periodic boundaries. How to select blending functions to ensure interpolation, and how to add further degrees of freedom for editing the interior shape. So these are our basic questions. So this is the Bezier talk. So let's talk about generalized Bezier patches. We start with convex polygonal generalized Bezier patches. Then we moved on and tried generalized Bezier patches for concave polygonal domains. Then we moved on and tried curved domains with holes. I will talk about that as well. And finally, there is a new member of the family, the template generalized Bezier, and I will talk about that as well. So let's start with generalized Bezier surfaces first over convex polygonal domains. Well, the idea is fairly simple. We can reinterpret the tensor product Bezier patches. You know this formula, control points, Bernstein basis function, and we can consider this as a rotationally symmetric arrangement of four half Bezier ribbons. So just take these 3 by 6 half Bezier ribbon, 3 by 6 half Bezier ribbon again. There may be coincident control points as well, but the main issue is that we can introduce local side and distance parameters. So the side parameter runs longitudinally, the distance parameter runs transversally. So there are four pairs of local parameters, and then we can reformulate this equation. So see this, I runs from 1 to 4, D is the degree, and L denotes the layer. So how many layers you have. In this particular example, you have 3 layers of control points. Now, once you have this tweak formulation, practically what you do, that you create a rotationally symmetric arrangement of 5 half Bezier ribbons. You have to introduce local side and distance parameters with circular indexing, and we will talk about this in a minute. But fundamentally, you have the multi-sided equation. You sum up 5 half Bezier ribbons. And actually, the generalized Bezier patch can be nicely coupled with the ribbon logic. So here you can see various Bezier ribbons, arbitrary degree Bezier ribbons. You can degree elevate to the highest degree D. You can insert interior control points, yellow and blue. And then at the end, you get the final representation, what I showed you before, the unified spider web control structure. Now, let's move on and talk about parameterization. So you need to determine some side and distance parameter. You want the SI lines to sweep from the I minus side to the I plus side. And then you want the H, the distance parameter, to sweep from the base edge to the remote edges. So this is the parameterization you want. And fortunately, these parameters can be computed from generalized barycentric coordinates. Well, here you can see the formula. So this is really very simple. Once you have barycentric coordinates, then you can compute the local side and distance parameters. Now the second issue, the blending function. Here you can see that there are mu-j terms that are Gregory-like terms. These are incorporated into the surface equation. Now, we can interpolate if, due to the Bernstein functions, the ice ribbon will disappear, will vanish on the remote side. And due to this mu, the ice ribbon will vanish on the adjacent sides. So it will have no effect on the I minus side, on the I plus side, and then the Boltzmann functions will vanish on the removed sides. So this is how interpolation is guaranteed. Now there is another important issue called weight deficiency. If you sum up the blending functions, see this expression, you will see that the sum of the blending functions, they are not necessarily one. Typically, it's not, it's not equal to one. But you want to ensure convex combination. So you introduce the weight deficiency. This is this B0 blending function, which is 1 minus the sum of the blend functions. Having this blending functions, you can introduce a central control point, which is free to choose. And in this way, you can enforce the convex combination. Let me show you just some sequences how GB patches work. Uh, just modify control points, and you can see that these are nicely distributed curvatures. And also another sequence here, degree elevation for GB patches is quite uh, similar to that of the tensor product Bezier patches. Again, you can see the sequence, so it behaves like an ordinary quadrilateral Bezier patch. Okay, a few example, and then let's move on to the curve domain generalized Bezier patches. So why we need curve domains? Well, there are basic problems with the convex polygonal domain. If you want to map a convex corner, uh, a convex corner to 3D, where a concave angle needs to be represented, it's a trouble. If you have a straight line in the domain and you want to map this in 3D, here you have a strongly curved concave 3D boundary, it will not work. It simply will not work. You need a domain where there are curved boundaries in the 2D uh, domain plane. And this curved domain should mimic the 3D boundary configuration. So you can see here that having the curved domain, you get a reasonable patch. Here, you get a reasonable patch. Let me show you a few more examples. Very simple example. Look at the ribbons with convex polygonal domain. You get this surface turns backwards, forward backwards. If you have the proper domain, you will get this surface. Another example, again, a curved boundary. If you use the polygonal domain, it will not work. However, if you use a curved domain, it nicely produces a surface. Well, you can see this with some animation. Polygonal, bad. That's good. Polygonal, bad. This is good. So this is what you expect. And clearly the parametric distortion, let's say we define this by the Arab energy, this will be much better. So once you have the curved domain, then it will be less and less parametric distortion. Now, the basic issues, how you create your curved domain. You can polygonize your boundaries, and you can use the local tangent planes and project the neighboring points into the plane. And then you have uh, planar polygons in the plane. You will get an open polygon that needs to be somehow closed. And you do this correction by playing with the lengths and the angles, and when you close it, you have the curved domain. The other issue is how you parameterize. Again, the previous parameterization will not work, but fortunately, we can compute the side and distance parameters as harmonic functions. This is a continuous problem that can be discretized, and eventually you have to solve a discrete Laplacian equation. Then you get a nice S and H parametrization. And also, this approach can be generalized for handling periodic curves. So here you can see a parametrization for a whole loop. Now, the surface equation for the curve domain patch is somewhat different. Here you can see that we have n plus nl ribbons. NL stands for the number of loops here. Then here you can have various DI for the individual ribbons, and here you can have various layers for the individual ribbons. Now the sum of the blends, again, it will not be one, so you have to do something about this, and you can ensure convex combination by normalization. So remember that the CDGB patch is somewhat different and it's fundamentally ribbon-based. Few examples, of course, set the vertex blend compulsory. Other example, the iron model. Here you can see the input. Here you can see a domain that was generated based on the boundaries. And here you can see the actual surface with the whole loop. And here you can see the CDGB patch. Now, if you try to compare the generalized Bezier and the curve domain Bezier, you will notice that here we have convex polygon, here we have curve domain. The shape is somewhat limited, but this is fairly general. But the general Bezier has the advantage that you can edit the interior CPs. The CDGB patch is not ready for fully defined, so you cannot do editing. And the question is, what can you do? We want to keep fairly general shapes, and we want to edit by interior CPs. So the next topic is template GB patches. The basic advantage of CD-GB patch is that the interior of the patch is fully defined. So you don't have to fiddle with interior control points. The patch is ready. Now, the basic disadvantage is that the interior of the patch is fully defined. And you may want to add some interior control for shape editing and fairing. So this motivated that we created a quad dominant control structure with a naturally distributed set of integral control points. And this is the template Bezier patch. Let me explain to you how this works. So here you can see the domain, and here you can see the HI isolines associated with the individual boundaries. Then we move on and we compute the parametric medial axis transform. Let me emphasize, not the Euclidean, the parametric medial axis transform, which means that this edge is the locus of points that for each point, the parametric distance from boundary I and boundary J, the parametric distances are equal. Or for this vertex, the parametric distances from this boundary, and this boundary are equal. So this is the parametric medial axis transform. And once we have it, we can drop SI isolines to the individual boundaries. And this gives us a nice structure, a nice quadrilateral structure. So this is the initial structure, the initial template. And here you can see that in the middle, there is a skeleton. Now, we call this D2 or quadratic structure because this is a template. If you imagine that there are control points associated with this structure, then there will be the longitudinal Bernstein function associated with this. So, for example, this will be a degree 5 Bezier curve. The longitudinal Bernstein functions will be quintic, but the transversal Bernstein functions will be quadratic. Now, as you refine this structure, this is the D3. Now the transversal blend functions will be cubic. And here you can see that for odd number of uh, degrees, here you will get polygons in the middle. But as you move on, then again, for the even number, you will get back again the feature skeleton. So, for example, this is a quartic structure and further refinement. So until now, we have talked about topological structures only. So here we define the topology, but of course, this structure exists in 3D as well. And here you can see this is, for example, a quartic patch. You can see three interior control points, and you can degree elevate in the usual manner that you define new control points in the interior of each quad, and then you connect the uh, adjacent points here. So this is D4, then this is a transition from D4 to D5. This is a transition from D5 to D6, and so on. Now, this is an important slide. You have to synchronize the input degrees and the template degrees. So on the left, you can see input ribbons with degrees. And then we compute the domain, and this defines a quad template structure, an initial topology. Now, in order to match this degree 7, you have to refine the template structure. So if you refine twice, then you will get a structure where now there is a perfect match here, and the remaining sides can be just degree elevated. So after a double refinement, you created such a template structure that matches your input. Got it? I hope so. Now let's move on and talk about blend functions. So blend functions are always Bernstein functions. Here you can see that there are control points associated with one boundary, for example, this one, or control points associated with two boundaries, or even there are control points in the interior that are associated with, in this case, three boundaries. Now we use biparametric Bernstein functions, and if there is more than one uh, associated boundary, then we will compute the average of these multiple blends. Now this is also an important slide because that explains to you how actually this scheme works. Here you can see the weight efficiency function, and then the weight efficiency is distributed by the three interior control points. And then the interior blends need to be normalized. So if you look at this equation, the left part, this is the sum of the exterior ribbons. This is the sum of the uh, interior control points, C. And then again, this is the weight deficiency, alpha sum. And you have to guarantee that the interior blend functions sum up to 1. So you need to normalize these blend functions. Let me show you a few examples. You can see that with the template, you get a better interior for our patches. You can also see that with minor editing of these interior control points, you can get a much nicer curvature distribution and reasonably nice isoforms. So this is possible. And in fact, this whole thinking, this whole family of patches can be generalized to B-splines as well, very briefly. So the GBS patches interpolate B-spline boundaries and cross derivatives. So longitudinally, we will have B-spline basis function. Transversally, though, it remains Bernstein. We can do periodic parametrization around the whole loops. And the math template concept can also be generalized. Moreover, we can generalize in a way that for GBS, template GBS patches, we can also handle whole loops as well. So let me show you a few examples. Jörg Peters' beautiful patches, the beam and the monk. This is just a network with four patches joined together. This is an example that, in fact, you can reach numerical G2 continuity. Originally, there were two layers of control points. We added artificially a third layer of control points and then numerically enforce G2 continuity. You can see that the isoforce lines behave nicely. Another example, a concept car and a fairly difficult patch. And then the template GBS, here you can see a surface. And here the idea is that you can refine this structure and then you will get many more interior control points. As an example, you can edit a test model and then you can modify the curvature in the below. Finally, a few more template GBS patches. So the fifth area is that of survey papers. I published an early paper on n-sided patches in 1987. Then we published a survey blending methods that use parametric surfaces. I mentioned this reverse engineering paper, which is a magic, I think. And then we published recently this genuine multi-sided parametric patches survey. So this is it. And finally, let me call your attention that there will be a presentation by Peter Salvi, 30, 1:30, and it is about topology preserving polyhedral design with ribbon-based multi-sided patches. So the idea is that you have the control polyhedron, you may have concave angles, you may have holes, but you can create such a structure that you will have freeform patches with exactly the same topology. So for example, here you have this top face, two hole loops. At the end, you will get a GBS surface with those boundaries and with those holes in the middle. So please come and listen to Peter's presentation. Well, this is it. Thanks very much for your attention. Thank you very much. Great lecture. So, yeah, go ahead. Yeah. So I understand. Um, is here I'm focusing on meshing class structures in this view. Huh? And I see somehow it's bad. Um, this will focus for using on that. I think is finding so long practices what starts as what deciding practices. Mhm. Sparks is what sometimes see well, I would say yes. So in this particular case, you know, you have the structure and you want to work with the multi-sided patch. However, if you apply the MAT decomposition for this structure, then each multi-sided patch, each multi-sided multi-connected patch can be partitioned into quads. And then you will get something like you are dealing with. So it may be interesting to look at that, what you would create for such a structure and what we create with the MAT. So, well, again, in this case, we only use the polyhedral, nothing else. Uh, if we have a quad structure, we may try, to use your quad structure and create these sort of patches. That can be certainly an interesting experiment. Yeah. Thank you. Uh-huh. All right. You want me to go back to that? No, no. One basic deficiency of all these unsided patches is that not standard formulation. So if you want setback in a good modeler, then you need export. So in this case, actually, I would use your patches, some central split composite patch, because that can be exported. Unfortunately, uh, well, generalized Bezier will be nice. So it does work for this sort of stuff. Yeah, yeah. So well, I would suggest a compromise that uh, take a generalized Bezier, uh, retain the center point, retain the subdividing curves that create the division, and then use your patches and then your continuity constraint. That would be maybe the best solution. Yeah. Yeah, yeah. Clearly, it can be done by trim patches, but then you will not get the interpolating property. And also, it's an open issue whether the interior of that X nerves is nice or not. In many cases, it's wonderful, and in other cases, you will not like the result. So in this sense, our view is that the setback vertex blend is the natural thing, that you determine the end of the edge blend, and then there is sufficient space to connect, and then you do it in a natural manner, so it gradually vanishes. So we believe that setback vertex blend is the good philosophy to get a nice shape, and that should be then somehow approximated, maybe by the trim, maybe by the composite and patch, and who knows. 70. Yes. 70. 70. Yes, hear you. Yeah. Well, the real medial axis will not reflect the domain shape. So if you look at this tells you that the effect of this ribbon will go up to the middle, and the effect of this ribbon will go up to the middle. So with the parametric map, you really subdivide, you partition the domain in a fairly natural manner. Now, this wouldn't be true for the Euclidean distances. You would get a totally different structure. It's simply not good for n-sided patch representation, but this is good because it shows you how the ribbons are spreading over the domain. Does it answer your question? Thank you. How easy? Well, this structure works on the surface as well. So as you map the domain, this structure can be drawn onto the surface. So returning to your previous question, Conrad, so this quadrangulation actually can be uh, noticed on the surface, even the refined one. So that's again something interesting we may want to look at. Very much. Thank you.
Hi, Jinjiang, can you hear me? Yeah. So this is our first session, and let's welcome Jinjiang for his presentation. So now it is yours time.
Sensitivity goes from to sheet, step by step. We call this unarranged. The second goal is smart transport or OT. OT is about the moving mass. So sports has a mass. The likewise also have mass. The transport and gamma tell us how much mass moves from the point M to point N. Please notice social correspondence matrix is exactly a transport plane. They are extensive with interruption. This problem is easy to solve. We can use simple operations that are simple and fast. Here, the epsilon works like temperature. It controls the sharpness of the pen. People already have used OT for registration. For example, RPOT or ROPOT. They also share this form, but the two choices have no expectation. Question one is the cost. Why not just square the distance? There is no theory for it. Question two is the temperature. We must turn epsilon by hand for every distance. If it drops slowly, this method is slow. If it drops fast, the method gets fast. Furthermore, we answer the question. Regarding theorem, let me issue the file. This is a 2D example. The gray curves are outlined. Here, more than half of the points are outlined. Look at this result. CPD fails company. The error is 2000 grades. Look at the bottom group. It shows the power of each point. We call it volts. Red means strong volts. In the city picture, outlines their weight. It means they vote their weight votes, put their roles to organize. They could results away. So here is question, why does this happen? Here is our main results. Summary one says the east step of the CBD exactly identical of markup transport problem. In this problem, the close is very distance. The temperature is 2 sigma squared. The cloud measures are fixed. The room measures is weight. The other one, CBD, is doing optimal transport all the time. Sixer must teach us two things. Thing one, it explains the value. The plan constraints every touch point must receive one unit per mass. It includes every outlet. So we never turn off optimize. This is the true rule for this problem. Thing two, it gave us the right design. The codes should be the closer root of height. No good likely. The temperature should be 2 sigma squared. They are exactly the answer to the question before. Now let me show this with numbers. The use of point is shared in the total mass. It what means far from the results. On the plan country, every optimized mass gave us one unit in weight. The soft assignment is very this way. But I cannot make this way smaller. The total is always one. In this example, optimized was 5,000 from 47.5% of almost more than half. The result is wrong. Now the fix is clear. We show that the mass of the 5 points go to zero. From this is our method. We make two things. Fixed change comes from the silver. Change one. We remove the hard countries. We use K of penalties instead on the blue side. What does K of penalty do? It allows a mass to change but with a cost. For an outline, there's no good match anywhere. So it's cheap to pay the cost. Then its mass goes there. Outline is cut off. Change two. We use a culture black hole as a host. So, the automatic analyzing of CBT is key. Look at the bar on the right. Outline will drops from into zero. One more thing. The diplomas experiment tau equals 1 volt for all experiments. We do not need turning the experiments. Here is a format map. It's an EM, the same activity. In the E step, we build the cost matrix and we run general simple declaration. This gives us the transports and step we solve a problem with SVD. It will give us the R and T. Then we update sigma. Look at the bottom three. The start, the pen is solved. Then the sigma finite and the pen become a clear diagonal line. This line is a great matrix. Every step has a corresponding solution, so it's fast. A few talks in the algorithm. The flow is a diagram push and pull. Various updates. Then loop. Each step is falling to scaling steps. We can repeat them in a few times, and it's easy to implement, and it can run fast on the GPU. And again, we do not need turning the elements. We can just say the tau x equal tau y equal 1 for all experiments. Here we show the temperature and the ceiling of these. The three lines are the temperature of each method. The dashed line are the true result. It means the real distance between the match and the match points. Good temperature should follow the result. If the reason is large, it stays short. When the reason is small, it becomes sharp. We can see the CDD is a blue line. It drops too fast and it becomes sharp too early. So it blocks in the raw matches. RBUT and RPOT do not look like as the data work. The government the original follows the rest of. So we can say that the date for method are date drivers analyzed. Now here is transport and evolution. There is same story from the other movie. There are transport metrics during the iteration. On the right side is the dashed line in the online plans. This is one popular outlines. And the left is the true the inlines. The pipeline is CDD. We can see that the optimized plans they are dark white and the constraint keep mass in the because they must set the all plan units mass for all the clan. Now the meter is RPT, RPT. It has a better result, but still clean. The bottom is one method. After 25 iteration, our pen is totally clear. It shows that our method can remove the outlines clearly. Uh, Here we um, compare our method with three papers our beauty is needs 21. It fix the external and fix the role. Their terms are fixed and in CGF 22. Their external are designed by marking one uh, 0 to 9. And all methods are for three like this. Here is our experiments. The first one is the test in the sample body. In the latter plot, we increase the internet use. In the meantime, is CBD. And it fails after 20%. And the original experiment said always stay in the bottom. Means it's not good results. This we can see in the product rates, when even with 70% compromise, oil method still give a good results. There is our experiments in the model line 40. The second, we can say that this dataset has 40 categories. We add noise and cropping to the original data. And in this experiment, all method reaches the best results. And even better than the geo transformer and RPM net. There are many methods and they are trained in the date all methods are not need to train. Now here is we test it in our real application. So we collect 40 industry parts and we scan it, get the income, and then we to retest it, use our method and test for the method use the batch method. And we can see our method still is the best um, and due to the futures are public and the thesis and FGR many errors. And we go to the population the 10 days we get the intensity to tau x and tau y. We can see that in this picture, our results are not changed very big. So it means we obtuse x equal to y is 1 everyone, and that is okay. And in the 2D, we test the downside here. It means that our downside here is the best. And in the picture C, we test our sigma form is really useful, and the result shows that our design is the best. And in the part D, we show that if which tau y equal 1 or other thing will be different. The result shows that when the overlap is more than 60% of structure and no difference. And when the overlap is low, we can choose y equal 0.1 will be better. And then when we draw conclusion, And then conclusion, this work build a bridge between CBD and automatic transport. First, the third one explains why CBD fails. And one set country both outlines to keep the mass. Second, the base is simple. We use scale entities on both sides. Then the optimized mass goes to zero, and variance step still close for 3. The variance is the temperature, so the analyzing is automatic and there is no time. In the future, we are planning to extend this method to non-rigid restriction and to large point clouds. Now here is the main reference. That's all. Thank you very much. Um, this paper, this is the paper link and our code and our benchmark code are open in GitHub. You can see the QR code here. That's all. I have to hear your questions.
Thank you for Jean's presentation. Any questions? So I have a question. So sometimes in practical, we may have multiple point clouds, not just the two pair. So how can you deal with multiple point cloud registration? Just you need can you do some joint optimization for multiple point cloud, like more than two?
There was restriction that only allow one point to another point. And if we want to use it in multiple restriction, we always use the um, tools to restore select and then align the two vehicles and then align two vehicles. And finally, we got the multiple registration, but it's a simple idea. There are more ideas such as when we combine together, we will use other methods such as list square to minimize all all to get results, better results.
Okay. So thank you for the explanation. And any other questions? Okay, thank you, Jing, for your presentation. And yeah, yeah. So let's welcome next presentation.
Wait. ，Good morning, everyone. Today I will present our work, Point Engine, inversion by direct iteration for high-fidelity point cloud diagnosing. The main goal of this paper is to recover clean and detailed point clouds from lost 3D scans. In this talk, I will first introduce the diagnosing problem and the limitation of existing methods. Then, I will explain our point-in-D framework, followed by experimental results on both synthetic and real-world datasets. Let us begin with the introduction. Point clouds are widely used in 3D vision and graphics. As shown on this slide, They support applications such as autonomous driving, digital cities, virtual reality, industrial design, 3D printing, and game development. Point cloud data is mainly acquired from scanning devices such as laser scanners, lidar sensors, and connected depth cameras. Although these devices have improved repeatedly, loss is still unavoidable because of sensor limitation, object materials, lighting conditions, and environmental influence. This loss not only reduces visual quality, but can also introduce errors into little geometry processing steps. This is why denoising remains a long-standing and fundamental problem. The key challenge is that point cloud denoising is an air-poster problem. A single noise input more corresponds to multiple plausible clean surfaces. Therefore, a good denoising master must do more than simply move points to nearby positions. It should suppress noise, avoid regression to the mean, and over-smoothing, and at the same time, process sharp edges and fine geometric details in unordered point clouds. Balancing its objectives is difficult. Next, I will briefly review the most related methods. Single-step deep learning methods directly map a loss point cloud to a clean one through a single forward pass. For example, point filter incorporates geometric information to better precision shape features, where SDN treats denoising as entropy recovery and use an adaptive stopping stretch to reduce over-smoothing under high loss. These methods are usually efficient and simple. However, when trained with distance-based losses, they tend to predict an overshot solution, which kills regression to the mean artifacts and may blow sharp details. Multi-step methods try to alleviate the regression to the mean problem by refining loss point cloud. So multiple stages. For instance, iterative PFN use a multi-stage architecture with intermediate separation and straight PCF, most nothing with straight pace flows. These methods can improve detail recovery because they decompose a hard inverse problem into several easier sub-problems. However, they often introduce higher computational cost and more complex architectures. This slide is our motivation. In multi-solution regions, a single-step regression tends to converge to the conditional mean of all possible clean shapes. As a result, high-frequency geometry is sensible. One shot regression to a multi-step feedback process. We construct a degradation path from clean to loss point cloud, and during inference, we reverse its path step by step. In this way, complex denoising is decomposed into either local restoration problems. Our contributions are threefold. First, we propose point ending, a new iterative point cloud denoising framework based on the inversion by direct iteration paradigm. Second, we introduce a continuous degradation path in point cloud space, together with a time-conditioned network for progressive refinement. Third, so extensive experiments on statistic and real-world data sets, we saw that point id achieves set of the other or highly competitive denoising performance while receiving geometric details. Now, let us move to the method. We first analyze why single-step regression may fail. Under distance-based losses, such as squared error or chamfer-like losses, the risk minimizer is the posterior conditional mean. This is optimal when the posterior has a single dominant solution, but in point cloud denoising, the posterior can be multimodal, especially narrow edges, thin structures, and ambiguous regions. In that case, the conditional mean reaches different plausible surface, producing broader geometry and loss of details. This is the regression to the mean effect. Here is the overview of point indi. During training, we randomly sample a degradation level T, constrict an intermediate state between the clean point cloud and the loss point cloud, and train a time conditioned unit to predict the clean state. During inference, we start from the loss input at T equals 1 and perform estimatic update steps. At each step, the network predicts a clean estimate, and a closed form update moves the current state towards that estimate. This gradually reduces loss and mitigates regression to the mean. The first component is the continuous linear degradation path. We define T as the degradation level. When T is 0, the state is the clean point cloud. When T is 1, the state is the fully lost point cloud. For any intermediate T, we linearly interpolate between the clean and lost states. This gives the model especially guidance about how geometry degrades from clean to loss. More importantly, it provides a simple path that can be reversed during inference. The denoising network is conditioned on both the intermediate point cloud patch and the scalar degradation level T. Its backbone follows a unit style encoder-decoder design, which is effective for multi-scale feature interaction. The time value T is encoded and injected into point features, allowing the network to adapt its prediction to different loss levels. Therefore, the same network can handle states near the loss end, intermediate states, and states close to the clean surface. The restoration process is divided into as discrete steps, and the step size is delta equals 1 over s. At iteration I, the degradation level is t equals 1 minus I times delta. So t gradually degrades from 1 to delta. At each step, the network predicts the clean point cloud from the current estimate. Then the closed form update combines the current estimate and the predicted clean state. As t becomes smaller, the update releases more strongly on the clean prediction, and at the final step, the current state is directly replaced by the predicted clean point cloud. The inference algorithm is simple. First, we interlace the current point cloud with the loss input and set the number of refinement steps. Second, at each step, we feed the current point cloud and the current T into the time conditioned network. Third, the network predicts a clean estimate. First, we apply the closed form state transition to update the current point cloud. After all steps are completed, the final refined point cloud is written as the denoted result. During training, the network is supervised to recover the clean point cloud from an interpolated degraded state. For each closed knot pair, we randomly sample T from a uniform distribution between 0 and 1, constrict the intermediate state, and ask the network to predict the ground truth clean patch. The loss is an L1 loss between the prediction and the clean point cloud. This objective encourages the network to learn restoration at every degradation level, which is essential for stable iterative inflation. Our method is guided by a clean degradation process and has a simple, more efficient network. Next, we evaluate point int experimentally. This slide shows visual conversions on the PUNet dataset. The color map indicates the point-to-mesh distance, where blue means closer to the ground truth, and orange means more north. Compared with the baselines, our result contains fewer orange arrow regions, and better preserves the overall shape, sharp boundaries, and thin structures. It demonstrates that point int can remove noise while maintaining high fidelity geometry. Here, we saw results on the real scanned connected set. Real sensor noise is more complicated than synthetic ghost noise. In contrast, our method generates cleaner and more uniform point clouds. We also test on indulgence. Point int generally well to answer real-world indoor data, not only to object-level synthetic benchmarks. This slide presents outdoor results on a street dataset, as shown in the highlighted regions. Our method removes heavy loss while preserving the structural shape of objects. After the visual comprehension, we further report the quantitative matrix. We use chamfer distance (CD) to measure the bidirectional distance between the denoted point cloud and the ground truth point cloud. We also use point-to-mesh distance or P2M to measure how far the denoted points are from the ground truth mesh surface. This slide shows the results. Shows the quantitative results on the PUNet benchmark on the different resolutions and noise levels. Overall, point int achieves best or highly competitive performance across more settings. This slide shows quantitative results on the real scanned Connect dataset. Point int achieves the best scores on both Connect V1 and Connect V2. Finally, we compare model complexity and inference efficiency. Now, I will conclude the presentation. In conclusion, we propose point int, a deterministic iterative framework for high-fidelity point cloud diagnosing. The framework progressively restores those point clouds along a continuous degradation path. This design helps mitigate regression to the mean artifacts that commonly appear in single-step regression methods. requirements so that PondIndy can recover cleaner surface, resolve sharp and fine geometric details, and achieve strong performance on both synthetic and real-world datasets. Thank you very much for your attention. I would be happy to answer any questions. Mm. Uh, our network is shown in the not narrow percentage. Point is one. Our network is shown in the percentage one loss and two percentage uh three loss. Uh, in the high level loss, our network should be retraining because the loss level is important for network. We show the 10K points and 50K points is to parallel the other business. In the 100K points, our methods can uh, our methods have also have a good performance. Uh, According to our fraud interpolation formulas, clean point clause are not required during testing. Only the agree the, only the agreed not point clause are needed. This is because the network has already learned the degradation path from clean to not point clause during training, and our network does not need to be retrained when faced with unsigned models. Mm, that's a good question, but I am sorry I can't give you a perfect answer. Uh, Perfect answer right now. But we can have a more in-depth discussion later our lunch. Okay. Uh, I I can understand some features. Uh, our network gives the model uh, a duration a, a duration path. Its duration path can can precisely guarantee the model to perceive the sharper features because the sharp features uh, can be perceived by this formulation.
Hello, everyone. My name is Guan Li, and today I will present pose fusion, a method for multi-view reconstruction from multi-pose captures. The problem we focus on is simple but important. In many captures, the camera can move around the object, but the object itself stays in one pose. In that case, the front and the side regions may be reconstructed well, while the bottom and the contact regions and self-occluded parts are still missing. Post-fusion address this by using several object poses. We first reconstruct one neural implicit surface for each pose, as shown in the figure left, the three poses of this Lego trunk. Then align this pose-wise surface and finally fuse them into one more complete surface. Before introducing my method, I first placed this work in the history of multi-view synthesis, in short MVS. Classical MVS methods, such as COMAP, mainly rely on explicit geometry. They estimate camera poses and then use multi-view consistency to recover point clouds or meshes. More recent methods, such as NERF and NEWS, use neural scenes representations. They optimize the continuous field through image rendering losses and other losses, which makes the reconstruction process differentiable. Later methods further improve the training speed, rendering speed, or surface color quality. Here, we can see the rules of multi-view capture and neural rendering. Multi-view capture provides geometry constraints. When the same surface is seen from different cameras, parallax and view consistency help us estimate its 3D position. Neural rendering provides the representation and optimization process. We render images from 3D field and back compare them with the input images and update the field use image loss.
The combination of this is powerful, but it still have a clear limitation. The supervision comes from visible surface is only. If a region is hidden in all input views, the rendering loss cannot reliably recover it. This is a limitation of single-pose multi-view reconstruction. If we take many images from different camera views, the object remains in the same physical pose. For regions such as a bottom, contact areas, or self-occluded parts, more camera views may still not reveal the missing surface. As we can show in the left three pictures as example, the back of this figure, the front of this figure, and the bottom of this figure are reconstructed badly because these are contact regions of the ground. This issue is not only the capability of neural network. The more fundamental issue is that the data does not provide supervision from these regions. A natural solution is to change the object pose so that previously hidden surface can become visible. So we can see why multiple poses are useful. With one object pose, the reconstruction is accurate mainly in the observed regions, as showing the puppy in pose 1. When the object is rotated or flipped into another pose, different parts of the surface become visible. For example, the bottom of this puppy in pose 1 here and the contact region here in red is invisible or so it can reconstruct back. And when we flip this puppy into another pose, we can capture the missing part. This gives us the information needed to reconstruct a complete object. So the main challenge is then no longer only reconstruction itself. Now, it is how to automatically align the neural surfaces reconstructed from different poses and fuse them into one coherent model. So here comes our method, pose fusion. It has three main contributions. First, it formulates the problem of reconstructing one complete neural implicit surface from multi-pose, multi-view captures. Second, it proposes a coarse-to-fine registration pipeline. We use oriented bounding box, OBB in short, SDF values, and image features to register separate neural implicit surfaces. Third, the paper provides experiments on both synthetic and real captures. The results show that the proposed registration is robust and the final fusions improve the quality and completeness of the reconstructed geometry. And here is our pipeline. Our full pipeline has 4 stages. First stage, for each object pose, we train a separate neural implicit surface. Second, we perform coarse alignment. The stage gives an initial rigid transformation between different poses. Third, we perform fine alignment. Here, image matches are lifted to 3D space and the alignment is further optimized. And here are the results of the coarse alignment and fine alignment. Finally, all poses are transformed into a common coordinate system, and the final fused surface is reconstructed from combined observations. And here are the fusion results of the whole object. Okay, let's move to the coarse alignment. The goal of coarse alignment is to provide a good initialization for large pose changes. The method first extracts a surface from each SDF and Q computes its OBBs. An OBB has 8 vertices with 3 possible axis correspondence, so we can emulate 24 candidate rigid transformations. The key point is that the method does not just choose a candidate using only SDF samples. It also evaluates the image feature similarity. A good candidate should map one surface close to the zero level set of the SDF after applying this transformation, and its corresponding views should be similar, have similar image features. Notice that we do not refine L course, but search for the minimum L course from 24 candidates. This makes the course alignment more reliable. After coarse alignment, fine alignment reduces the remaining local error. The method first selects the image pairs that are likely to have overlapping visible regions, like this. It then uses eLoft to extract 2D correspondences between image pairs. After that, we lift them into zero-level set of SDF using ray tracing to 3D space. The final optimization uses SDF consistency, that's SDF loss, and the formulation of the transformation, L rotation. In this way, the two pose-wise surfaces are aligned better than the coarse stage. This slide shows the effect of the fine alignment. On the left, different pose-wise surfaces still have visible misalignment after the coarse registration. After the fine alignment, sorry. After the fine alignment, the local structures match much better. The curve at the bottom shows the SDF loss decrease during the optimization. The main message is that fine alignment is not just a small post-processing step. It is important for removing residual errors. Without it, the final fusion may contain ghosting, duplicate cases, or local offsets. Okay, after introducing our method, here comes the experiment part. Before showing the experiment result, let me introduce the dataset for evaluation. It included 11 synthetic models and 7 real-world captures. The synthetic data provide ground truth, so it can be used for quantitative evaluation of rotation error, translation error, and final geometry quality. The real captures are used to test whether the method works well under practical scanning conditions. The average registration time is 4 minutes and 30 seconds. This includes both the coarse and fine stages. For offline reconstruction pipeline, this cost is acceptable. And this slide shows the registration results. The different colors represent the reconstructions from different object poses. The goal is to align them into one common coordinate system. The examples include large pose changes, complex topology, and self-occlusion. Post-fusion still produce consistent alignment in these challenging cases. However, in contrast, several baseline methods such as REGNF, Dirac-Nerf, or Gauss REG are failed to register the certain cases because different reasons. The summary metrics on the right show that the rotation and translation errors remain very low after the registration. And this supports our main design of the choice. Robust coarse initialization and fine correspondence-based refinement are both needed for the setting. After registration, the final goal is the fusion quality. The left picture compares the input, the ground truth, and the fused geometry and individual pose-wise reconstructions in these colors. As we can see, the fused geometry is the closest to the ground truth mesh, while other single pose reconstruction remains some artifacts. A single pose may reconstruct some visible regions very well, but hidden regions are still incomplete. The fused results use enough observations from multiple poses, so the overall geometry quality is much better. These three metrics on the top also support our conclusion. The fused results have lower transformer distance and higher normal consistency and the F-score. The main point is that no single point is always enough. Fusion uses evidence from all poses to obtain a more stable surface. We can see the comparison on the right side video, which shows all single pose results have somewhere reconstruct badly. The bottom, the back of this single pose, and the front of the pose 3. And here comes our ablation study. This ablation study explains why both registration stages are necessary. If the coarse stage is removed, the optimization has no reliable initialization. With large pose differences, it can easily convert to a wrong alignment, so the method fails, as shown in the subfigure B. With large pose, if the core stage is kept but the fine stage is removed, the object is roughly aligned, but local residual errors remain. These errors are still harmful to the final fusion. The full model combines coarse initialization with fine refinement. This is why it produced the most accurate alignment in the example showing subfigure C, D, and E. And E is a close-up view. Our method is robust in many cases, but it still has some limitations. The first limitation is ambiguous OBB orientation. For symmetric objects or nearly symmetric objects, not only in its geometry but also in its color, as we can see in this synthetic and real-world case. The OBB have several plausible directions, as shown in the 3D space example and 2D space example. In such cases, the coarse stage may choose a wrong orientation and the fine stage may not fully correct it. The second limitation is insufficient overlap. Fine alignment depends on the image matching and overlapping visible surfaces. If two poles shares almost no visible region, the matches become unreliable. Therefore, pose fusion works best when the poses provide complementary coverage while keep some shared visible areas. And we can see in this subfigure, A and B can refine after the course registration, but A and C cannot because this shown in D and E, this is only front and this is only back view, so they have shared nearly no visible regions. Okay, let's have a quick summarize. Pose fusion address the missing geometry problem in single pose multi-view reconstruction. Multiple poses reveal complementary hidden surface, and the key is to align and fuse pose-wise neural fields reliably. The method uses OBB, SDF, and image features for coarse registration and fine refinement. It then uses 2D images matches leave to 3D for the fine alignment. And finally, the aligned observations are fused to produce a more complete geometry. The QR code on the bottom links to our project page where more results and visualizations are available. Thank you for your listening, and I'm happy to answer any questions. I have a question. So, for foods that have foods. Mm. Mhm. So, yeah. It's kind of different. For the mesh itself, it's likely equal, and we have tested whether fuse all the visible regions and the SDF of different poses use the registration results, or fuse the original data set and retrain the fusion neural implicit surface. We further imply the second step because after the further training, we can render the unvisible regions. If just a few the SDF fields, we cannot, for example, suppose one, we want to render that, we cannot do it. So if you want just a complete mesh, fusing the SDF is enough. But if you want to see the all kinds of view of the object, you need to fuse the original data set and retrain. Yeah. Oh, yes. In this, it can be split in two cases. The first case is OVB is ambiguous in, for example, this cubic. This cubic, of course, have multiple plausible OVB as also shown in this failure case, but we can rather it successful because it have different face colors. So the image feature can solve that. However, for these failure cases, for example, this toy and this synthetic model, the image feature is also similar when you viewing it in the same direction. So we cannot solve this problem in that case. So that's mainly depends on whether the SDF SDF or determines OBB or the image feature. One of them is different post-fusion can register them successfully. If both of them is unavailable, have plausible settings, our method may fail.
All right. Good morning. Thanks, Tony, for the introduction. So in this talk, I will present GSurf, which is a hybrid differentiable random method for multiple reconstruction. And this is a joint work with my PhD students, Baixin Jiaze, as well as my former postdoc research fellow, Jiang Bei. So in fact, this work is complementary to the previous talk, post-fusion. So in post-fusion, it goals is to reconstruct high-quality surfaces from multi-view and multi post captures. Okay, the registration step itself is efficient, but the reconstruction step is quite time consuming because it relies on volume rendering. So in fact, this work is complementary because it has two purposes. Firstly, we want to maintain the high quality of the reconstructed geometry of the surfaces. And secondly, we want to reduce the training time. Okay. So let me begin with the problem statement. So here we are given several RGB images of an object or a scene as input, then together with known camera poses. Our goal is to reconstruct a clean 3D surface. The multiple reconstruction is a classic research problem in 3D vision. It has been studied extensively for a few decades. And traditional reconstruction pipelines, which typically are based on computer vision techniques, mainly use the structure from motion and multi-view stereo. So the basic idea for these classical approaches is to match pixels across different views, then estimate depths, then finally fuse the geometry. And these methods can typically generate very dense point clouds, then from which we can apply surface reconstruction tools like Poisson surface reconstruction to obtain polygon meshes. So, however, these methods also have limited capability in terms of appearance modeling. And the reconstruction quality may be low because we can see artifacts such as holes, noise, or inconsistent geometry. So this actually motivates learning-based approaches for multiple reconstruction. Neural radiance fields or NERF, developed by Mildenhall et al. In ECCV 2020, was a major breakthrough for novel view synthesis. So here we're giving a sparse set of images and known camera poses as input. A NERF learns a continuous volumetric representation of the entire scene. Then by volume rendering along camera rays, NERF can synthesize very high quality novel views from arbitrary viewpoints. So basically, NERF is very strong for rendering. But the important question is, does this also give us accurate surface geometry? And the answer is not directly. So NERFs actually can learn radiance and density fields, and these two are very good for rendering purposes. However, they do not explicitly represent a surface. So usually, if we want a mesh from NERF, we need to threshold the density field. But this threshold typically is very hard to choose. So here, if you see this skull model from the famous DTU benchmark, you see that if we set the S value of the density field, sigma equals 1, 50, and 500. So none of the extracted SO surfaces represent a clean, high quality geometry. And also the density fields is often very noisy. So volume rendering basically can tolerate this noise because volume rendering is based on integration. This integration nature allows volume rendering to integrate along rays and can hide some of this noise in the final rendered images. But if our goal is to reconstruct a surface from the density field, then this noise becomes visible. So they cause artifacts and inaccurate geometry. So NERF is excellent for view synthesis, but it is not ideal for if our final target is clean, high quality surface from the multi-view images. So to address this problem, neural implicit surface methods such as NUS and volume SDF introduce an explicit surface representation into the neural rendering pipelines. And they replace the density field with implicit functions, usually a scientific field or SDF. So an SDF is useful because the zero level set directly defines the target surface. It also allows us to define regularization. Such as use the external external constraints, which is the first order constraints, or even using the singular Hessian constraints, the second order constraints. So this regularization allow us to obtain smooth, high quality geometry. And these methods jointly optimize appearance and geometry, so they can produce much cleaner surfaces than basic NERF. But these methods rely on volume rendering. So this means that they still need many resamples and many MRI queries in order to produce a single image. So this can be very time consuming. So neural in place surfaces give us high quality geometry, but they're slow. For a typical scene in the DTO benchmark, training may take more than 10 hours. And to be honest, this is very slow. This is very slow. So this creates a trade-off. We can get very high quality, strong geometry quality, but the efficiency is limited. So this motivates our work. Can we keep the geometry quality, but greatly reduce the runtime? So this is where Gaussian splatting becomes attractive. And 3D Gaussian splatting represents a scene using many local Gaussian primitives. So instead of sampling densely along camera rays like in volume rendering, so 3D Gaussian splatting projects these primitives to the screen space and then use alpha blending to compute the pixel colors. So this can be implemented very efficiently with CUDA rasterization. So training is much faster comparing to volume rendering-based approaches, and rendering can also be done in real time. But there's one key limitation. So these Gaussian splats do not inherently form a continuous surface. They're discrete. So 3D Gaussian splatting is very efficient, but the geometry is not as clean or explicit as an SDF. Now we have two useful ideas. Okay, so on one side, neural-linked surfaces give us a continuous SDF geometry. Okay, but they're slow because they rely on dense volume rendering. On the other side, okay, Gaussian splatting is very fast, okay, but the Gaussian primitives alone do not define a continuous surface. Okay, so the key question is, okay, can we get continuous SDF geometry without reintroducing volume rendering? Okay, so this is the key question. And GSurf actually answers this question by moving SDF supervision directly into the splatting branch. So this slide gives the high-level idea of GSurf. So we introduce SDF inside the 3D Gaussian splatting rendering pipeline, but instead of adding an extra volume rendering branch, we supervise the SDF directly using Gaussian primitives. Okay. The main challenge is that Gaussian centroids must be reliable. Okay, imagine if the Gaussians are not very high quality, they're noisy, they are semi-transparent, or they're just float away from the surface. Then these Gaussians actually provide very bad supervision, which can mislead SDF learning. Okay, so GSurf, the main goal for GSurf is to make these Gaussians reliable enough so that they can act as surface anchors. And this slide shows the four key components of GSurf. And firstly, we treat Gaussian centroids as candidate surface anchors. And secondly, we use opacity entropy regularization to push the opacity towards two ends. Okay, either 0 or 1. Okay, 0 means these Gaussians are completely transparent, so they can be ignored. And 1 means that they're opaque. Okay, then we'll apply a threshold to filter out all low opacity Gaussians. And thirdly, we supervise the SDF so that the reliable Gaussian centroids lie exactly on the zero level set. Last but not the least, we use SDF normals and the geometric features to help with color prediction. Okay, so the key design choice is SDF learns from reliable 3D anchors, not from the actual remarching based volume rendering branch. Okay, so this is the main reason that GSurf is able to keep the efficiency of 3D Gaussian splatting. And this is the whole training pipeline. Okay, so the image reconstruction loss optimizes the Gaussians from the multi-view images with the RGB color as supervision. Then at the same time, we have the entropy loss. Okay, so this loss pushes opacity towards two ends, either 0 or 1. And this loss helps remove weak transparent primitives. Okay, then in the remaining Gaussian centroids are used for supervising the SDF zero level set directly. Okay, and the SDF also provides useful information like normals and geometric features. So we use these features, we feed these features into the appearance module to predict better view dependent colors. So everything is optimized within a single splatting branch. Okay, we do not use a separate volume rendering branch. Okay, this is actually the key difference between our method, which is actually a hybrid method between Gaussian and volume rendering. Okay, there are other existing approaches with uses SDF and Gaussian together, but they have two branches. Our method only relies on one branch. And we have one practical issue to consider in our experimental results and implementation. Okay, so we call this a cold start problem. So at the very beginning of the training, we observed that the initial Gaussians, which are typically from structure for motion or even from random initialization. So these primitives typically are very noisy. Okay, if we use them directly to supervise the sun density field immediately, then the SDF may learn a wrong surface. Okay, so in our implementation, we consider this so-called a cold start strategy. Okay, so we delay SDF activation. And in the warm-up stage, the image loss and opacity regularization first clean up all Gaussian primitives. All the local opacity primitives are removed. Okay. Then after that, the SDF sees more reliable anchors and training becomes much more stable. So in our implementation, this delayed activation starts SDF learning after the first 500 iterations. Okay, so we use this hyperparameters for all the experimental results in our paper for the DTU dataset and MIP NERV 360 dataset. And this strategy helps avoid early optimization collapse. And this is actually one of the core ideas in GSurf. Okay, so low opacity Gaussians, they may not affect rendering very much, okay, because rendering is actually based on alpha blending. If a Gaussian has low opacity, so it does contribute little to the final pixel color. However, these Gaussians may affect SDF learning significantly. Okay, this is because as SDF treats these Gaussian centroids as surface samples. If many centroids are just floating in the space, they're not on the surface, then SDF may learn around surface. Okay. So GSurf uses entropy opacity regularization to push Gaussians towards being either opaque or transparent. Okay, so the density is at just zero, opacity just 0 or 1. Okay, and then low opacity Gaussians are filled out. Okay, then after this, the remaining centroids become much more reliable because they can serve as surface anchors. In our experiments, we observed that, okay, so this strategy is highly effective in terms of reducing transparent Gaussian significantly. Okay, so here so if you check, where's the pointer? Okay, if you see the bar chart, okay, the bottom one is our full model. Okay, so the number of transparent Gaussians with threshold below 0.5 is only 1,000. Okay, the overall number of Gaussians is more than 43,000. Okay, so this ratio is extremely small. If you check the baselines, for example, the 2D Gaussian splitting, okay, so the number of transparent Gaussians is significant, okay, 24,000 comparing to the remaining one, which is 36,000. Okay, and also our ablation study justify the effectiveness of this regularization. And this conversion table is very dense, so I would not read every entry. And here, the main thing is just the final row, okay? So compared with other GS plus SDF methods, to be honest, there are many other methods which consider using both Gaussian splitting and Sandison fields together. Okay, so comparing with these approaches, so GSurf keeps a single splitting branch. Okay, all the other methods, they adopt two branches. They use Gaussian splitting as well as volume render together. Okay, and GSurf has only one branch, which is based on Gaussian splitting. Okay, so it supervises the SDF at Gaussian centroids, then also use geometric regularization, okay, such as a Kano and normal regularization. And the time complexity, okay, is proportional to the number of Gaussians, okay, instead of the number of rays multiplied by the number of samples. So that is the complexity for volume rendering-based approaches because we avoid volume rendering at all. So our time complexity is proportional to the number of Gaussians. And from the results, we observe that the number of Gaussians is a few. Okay. So here, the message is GSurf is able to keep the efficiency of splitting while still learning continuous SDF geometry effectively. Okay, so let me show some real results. And this slide shows 3 representative models from the DTU benchmark. And in many baseline methods, we can see artifacts like holes, noise, or fragmented surfaces. And GSurf gives smoother and more complete surfaces comparing to the baselines. And also GSurf can preserve important geometric details thanks to the use of Sandison fields. So the main takeaway is that GSurf achieves a better balance between geometry quality and efficiency than the baseline methods. And GSurf is not limited to object level reconstruction. So here we also show indoor and outdoor scene level results. So compared to with GSPOO, which is a method published in NeurIPS 2024. Okay, so GSurf actually produces surfaces that are less fragmented and preserve finer structures. So this actually demonstrates that GSurf can scale beyond isolated objects to more complex scenes. And this ablation slide shows why opacity regularization is critical. Okay, if we remove geometry guided appearance, okay, so this actually only causes a modest quality drop. Okay, but if we remove opacity regularization, so we see a significant quality degradation. Okay, the chamfer distance actually increases from 8.97. Okay, this is for the full GSurf model to 21.83. Okay, so if we do not use opacity regularization at all. Okay, so this means that the anchor assumption breaks down when opacity is not controlled. So the entropy and the pruning design is not just a small detail. Okay, in fact, they are the key mechanism that can make the direct SDF supervision from Gaussing this process very stable. All right, so in conclusion, GSurf actually connects continuous SDF learning with discrete Gaussian splatting. And the main idea is to turn Gaussians into reliable surface anchors using entropy, opacity, regularization, and pruning. Then we can supervise the SDF directly from Gaussian centroids without adding extra expensive volume random branch. And finally, SDF normals and geometric features also help improve appearance modeling and geometric details. Our code is already online, so you can scan the QR code to access the GitHub page. Okay, and thank you for your attention. Actually, 500 is the experimental a heuristic number. So my students just simply try this. Yeah, actually, I didn't know whether if you change this 500 to 200 or 1000, so how come the result would be? I don't know. Yeah, so this is a purely experimental results, and this is heuristic. Yeah. So for all the detailed benchmark, and we try this 500, it seems it works pretty well. Yeah, but for other data set, some other numbers may work. Yeah, we don't know actually. Yeah. Yeah, yeah. This is standard one. Yeah. Actually, because here, good point. So for SDF is a key component in the whole optimization pipeline, and we supervise SDF by using Gaussian centroids. But we do not use all the Gaussians because some Gaussians may not be the ideal ones, so they may float in the whole space. They have very low opacities. So after removing all these Gaussians, then the remaining ones, we consider these are reliable geometry priors. So we train the SDF so that these Gaussians, okay, lie exactly on the zero level set of the SDF. Then, of course, to learn SDF effectively, we can apply regularization like Icano or some other regularization. Yeah. Next, please. Uh, I should ask my student. I don't know. Yeah, yeah. This is the implementation details. Yeah. I believe that it's just a single neural network for one escape. It's not hierarchical. Yeah. Mhm. Yes. Yeah. Mhm. We have the CD. Let me see if these numbers are the chamfer distance. These numbers are actually the number of Gaussians. Actually, in the paper, we have the quantitative metric. We have both chamfer distance and the normal consistency. Yeah, because these models are from the Omni 3D dataset, so we have ground truth geometry. Yeah. Okay. So besides the visual checking, so the quantitative metric also reveal the high quality of our approach. Yeah. Oh yeah, shock features. Yeah, yeah. Uh, uh, yeah, this is a good point. Yeah, actually, next week in SIGGRAPH 2026, we'll actually present a paper. That paper is called SharpNet. Okay, so SharpNet is a variant of the conventional multi-layer perceptron. So in SharpNet, we're able to represent exact perfect shock features within neural network. But this one, okay, this is just based on conventional MLP, so we do not preserve shock features. Yeah, so it looks sharp, but conceptually it's still smooth. Yeah, good point. Yeah, yeah, of course. Okay. Okay. Yeah, thank you.
Ses. Forgot. So much I forgot. Just can't remember that bit. Ah, when we got the music to this, my memory's gone.
Right.
Okay.
So what?
G.
Just I will do first and you will do second. Okay.
You can do
I will do first. Just listen and try to replicate first of all. Okay?
singing it.
No, it's not. You will not sing. You will just play.
Oh, I
Okay.
got
It's
it.
easy.
I'm not a very good ear player, but I have the music.
Maybe we can take a. Okay.
Give me a array.
Okay.
This array. So that's yes, but that's not the soul. But this is a dough. This is a dough here.
Okay, maybe different. Yeah. Oh, yeah.
Familiar with the English terminology. Yes.
Left, right.
Hello.
Canım veriyorsun. Niye? Bilmiyorum şimdi bir şey yap. Canım yapıyor.
What was this? So yes, it just so happens that something one of the team arranged it for me. The example
No.
just for you play with? No, I no, I play shot. Oh, I oh, shatters. My system's on the but it's in three part. So
Which one you play? Here, right? Yeah.
so I'm playing here.
Okay.
I'm singing here. Skoda.
Okay. Yeah.
That's or you're playing the melody then. So well, I think it's the same. Um, just in different octave. Yeah.
Okay.
We play that note together.
Correct.
Yeah, yeah. Oh,
Okay,
so,
correct.
yeah.
Yeah.
We're in the same.
Correct. Yeah. You say this is soul?
No,
This is
this is F. F.
yeah. This is a little different if compared to Turkish music. So four.
Four flats.
Yeah. Different.
Mm-hmm. Because I don't know how to pronounce these words.
Hmm. Correct. Yeah.
I don't know, but that's well. Okay.
But I think you have to use. This is different. I mean, there are three lines here, right? You have to choose the correct one. So we have to. Yeah.
There's a piano part.
Not piano part. Not the
Oh,
one.
you want me to
Okay.
sing the? I think is it?
Try another one. I will say. Okay.
But you have to.
Not that one. No.
I'll sing one.
Try the other one. Not that one. Try the other. There are three lines, right? So
Yeah. So
not that one as well.
this one.
No, not so. So we will. Okay. Correct. Once again. Correct. Once again, okay, from the start. Okay, once again. I think you did very well. From the start, start once again. Yeah. Okay, ready? One.
I can't say the words properly. I know.
I think my students can sing.
You need one of your students to sing it. I can't say
Buraya getirsenize mikrofonu. Aldı da beni. Buraya buraya. Buraya da. Buraya da. Okay, very good. Once again, then we can do. Yeah. Yeah. Okay.
Some
One.
people have pronounced these
Okay.
words properly.
So from the start, we can do again. I think you can do it better right now. One. Of course, yeah.
You can sing.
Yeah. One. Ready?
Do you want me to make that mean?
Just one is enough. I think we can. You can use the top line. Top line. It will be better. Yeah. Okay. That one is harder. Yeah. Okay. We can try maybe. Okay. 1, 2, 3. Okay. I think we can do it. Yeah. Normally, so we do slowly, and then we go faster. This line like this, and the next time. Not sure. You. Olmadan yağmur Üsküdar gelirken ağlayayım Katibimin sesi uzun ece çam Katibimin sesi uzun ece çam Okay, very good. Yeah.
Does the cedilla change the C to a sh? So it's C cedilla.
Yeah, yeah.
Yeah.
Yeah. Let me check. So you're
Here, that's sh.
let me okay, I will sing. Where did you start? I will sing and maybe you can listen.
Yeah.
Okay, from here. Üsküdar'a giderken aldı da bir yağmur. I mean,
That's
this
not
is a
too
different
bad.
one.
Yeah.
Üsküdar'a giderken aldı da bir yağmur. And then, yeah. Same. Okay. Katibimin setresi uzun, eteği çamur. Katibimin setresi uzun, eteği çamur. That's it. So, so they repeat it 2 or 3 times.
I wasn't
Yeah.
so far off the.
Yeah, that's a great.
Okay, so what
Yeah.
does this mean?
When I'm going to Üsküdar, suddenly the rain drops, and Kadim is my love, probably like secret love. His secret love. Skirt is long. Stres neydi ya? Stres nedir? Okay, one piece is long. Okay, one piece is very long and it got dirty. Something like that.
All right.
Actually, it's describing some kind of secret law. Maybe only he knows.
Yeah.
The opponent doesn't know about it. Yeah, something. I'm sure this is one of the famous one. Yeah.
Oh, it is.
You can do like this. First, okay, V3,
Yes.
do it, and then after this, you can play piano
Yeah,
as
exactly.
you like.
I'd have to
As you like.
practice a bit.
As
Try to get
no,
my
no, no.
memory back.
No, I mean not this one, not
But-
this one, but the one you like
Yes,
can be
yes.
fine. Maybe we can put this today or tomorrow. Maybe tomorrow we can practice today, tomorrow afternoon.
Yeah, yeah.
Do you want to practice again? Or
Yeah, I have to practice what I'm going to play.
okay.
I can't remember the end.
Ya söylemiyorum zaten. Şöyle 10-12 yaşından beri çalıyorum ama bir ara aşırı şey yapmadım. Ama üniversitedeyken günde 4 saat falan çalardım yani. Yok ya ben burada çalmak
So what do you play for some?
the other one you say?
This?
I can play, I mean, instrumental is that?
How much does it cost?
Right now I am not sure about the prices. It's maybe costing not like this, yeah. This is actually in Turkish re, but I don't know, in your case maybe it must be sol. Sol, is it sol?
So try.
This is re in Turkish. Yeah. What's
G.
G? G is
G is so
sol. Yeah, sol.
This piano is slide here.
Yeah, that's you know the system is already invented by Hungarians.
Ah, really?
But that's you're talking about fixed.
No, the relative ones.
The relative ones.
Kodai.
Because I use the relative ones for thingy, but I don't know the fixed ones.
No, the fixed one is used by French.
Is it? Yeah.
Yeah. Okay. So I think you can practice what you will play tomorrow or today. I don't know. Yeah. You want to play? Yeah. Do you want to play here? You want to play this one? No? Şunu koyalım da be.
Administrative matter.
Yeah, why not? Yeah. There is my pen.
You also need stamp, I think.
Stamped by the department
Yeah.
something. Oh, okay.
So I could just leave
So,
it with you.
just a minute. Who? Not me. Okay, yeah. Not me.
I might have to use it for that.
Hmm.
Geliyor mu?
Şey fakültenin yani.
Okay. Okay, so tonight it's all night. Ses geliyor mu şu an? Ses. Yapacak bir şey yok.
It never goes. I don't have to use it. Anyway, when do we have a lot of what kinds of yes.
No, it's
Yeah, which one? Where? So name and signature, yeah. Yeah. Oh, this is on? No. Yeah, yeah. That's okay.
Well, we'll give people a few minutes.
Yeah, yeah.
Start on time, not to wait for people to get it. Quickly. Well, welcome everybody to the session on implicit modeling, which I'm very pleased to see. We've got a few implicit modeling papers. The history of implicit modeling is that we had a separate conference series called Implicit Surfaces way back in the 90s, and then we merged with shape modeling, and the rest is history. So, but I'm very pleased to see the area is still very active. And of course, having been retired for the last years, I have not read any of the stuff on neural implicit. So I'm very interested in the first speaker from India, which was certainly not one of the countries interested in this modeling back in my day. And it's very good to see that there is more discussion context. Otherwise, we could see in the French. So, Vinci here is going to be our first speaker. Vinci Anthony, co-authored with Fan Merget. Oh, I'm going to get this one. And he's going to speak on some of these neural SDFs, which I'm very interested in. Go ahead. Do you want
Yeah.
this one as well?
No, I can use this. Good afternoon, everyone. I'm Vinci Antonium from IIT Madras. My advisor is Professor Ramanathan Muthuganapathy. Welcome to my talk on BBSDF, which is focusing on creating generalizable neural SDF and middle access extraction from the learned field. So our input is unoriented, noisy 2D point sets. We assume no connectivity, no normals. Our aim is to learn SDF and then extract the medial axis. So before I move into the details, I would like to discuss what sign distance field is. A sign distance field assigns for each point its shortest distance to the boundary, with the sign indicating whether the point is inside, on the surface, or outside. So it is computed using this equation. It is straightforward to compute the sign distance field for analytical shapes like circles, sphere, etc. For example, for a circle shown here with center C and radius R, solving this equation will give us a value of negative sign distance value for a random point R, 0 for a random point R on the boundary, and positive for a random point R outside the boundary. So this shows the heat map representation of the sign distance field for a 2D circle and a 3D sphere. The difficulty that we face is we do not have a continuous boundary like this for which we can find the exact distance value. We have this kind of sampled points. For a random point R, the shortest distance shown by this black curve, that point is not even there in the sampled points. Another difficulty is we do not know the inside outside. So we can only find an approximate distance shown by this orange curve. So this becomes an approximation. So one can think of reconstructing the boundary and then computing the distances, which again becomes approximation. So here I show a 2D point set along with the approximated boundary. So this approximation itself is hard when the boundary is noisy. So as can be seen here. So hence our aim is, given a noisy point set, learn the sign distance field and then extract the medial axis. Currently, there are few approaches for learning sign distance field, but most of them are per shape optimization network. So they fit one neural network per shape. Hence, they are very slow and not do not generalize to all shapes. And moreover, as we saw in the morning talk, they focus on surface reconstruction accuracy (SDF) on the surface. So, leaving the interior SDF that is not given much attention. So, our aim is to learn the interior SDF accurately because that is what we need to extract the medial axis. And currently, there is no public data set with accurate full domain SDF supervision that can enable us to learn the sign distance field. Because people usually rely on regularizers like iconal, Lipschitz, neural pull loss, etc. But they are very slow. Our aim is to make faster network even in terms of training because we do not have big computing facilities. So we couldn't rely on all these slow regularizers. So we wanted to rely less on regularizers and rely more on data. So this is the aim. Given a noisy point sets, instead of taking this geometric route, this shows a Voronoi based skeleton. Instead of taking this geometric route, we go to the sign, learning the sign distance field and then extracting the skeleton from it. So the key contributions are an SDF dataset, which is a diverse 2D point set with accurate point to curve ground truth distances, and then a generalizable neural SDF architecture, which focuses on locally conditioning the network and hence predicting accurate far from boundary sign distance field, and then a medial axis extraction algorithm from the learned field. To create the data, we represent shapes using B-spline curves and then solve the constraint equation and then take the minimum distance to get the sign distance. So this shows an example of our data creation process. Here I have shown one shape using a B-spline curve C of t. Then for a random point r, we solve this constraint equation to get all the candidate point. And this is the minimum, this is the one with the minimum distance that becomes the precise sign distance for that particular point. So this shows for a point r outside. So this shows our we have shown for 1,000 samples the sign distance value. This shows the heat map representation of our ground truth data for one sample. Following this process, we created 1,176 curves and we store them as boundary points, 1,024 boundary points and 50K random points from inside, outside and on the boundary, which serves as our ground truth data. So this is the algorithm that describes the data creation process. Then we created a generalized neural network architecture. So what we do here is, given a shape, we encode it using this network and this goes to a feature grid. And then when you want to predict the sign distance for, let us say, a query point Q, you sample the feature grid at that location. So this will give a local context of what that shape is. So now you have conditioned that point on the shape itself. Okay, now this shape information, so this is the shape information, which is a feature vector, along with the points coordinate xyz, xy in this case, at that point is Fourier encoded. These two are concatenated and given to a multi-layer perceptron, which predict the sign distance value at that point. So this is trained on all the 1,176 training shapes that we created. So you can see the predicted sign distance field already has the medial axis coming out of it. The divergence of the field is used to create a score using which we extract the skeleton. This algorithm explains the SDF, the skeleton extraction process. So these are our results. We are shown as 3 columns. The first is the input point set. Second is the predicted sign distance field. And third is the extracted skeleton from it. We have shown for various shapes like organic shapes, thin structures, junction cases, high curvature, etc. So This shows result for shapes with holes, which is not even present in the training data. You can see blue represents the sign distance value for shape in the inside, and red represents the outside, and from which we extract the skeleton. So it may be noted that this was an out of generalization data. We never saw this kind of data during training. So this is a comparison with existing neural approaches, the neural skeleton, the deep medial field. This grid-based approach is not a neural approach. It is the usual grid approach of finding the distances, a one-leaf sheet approach. And this is our method. This last column shows the ground truth. You can see in various noisy configurations and outliers, and even in missing regions, we could produce stable sign distance field. The neural approaches are also good in predicting the sign distance, but grid-based approach fails in presence of noise. You can see this result. So, major drawback of the per shape optimization approach is their time required. We predict in one forward pass in only 0.18 second, while most per shape optimization approaches require multiple iteration because they fit one neural network per shape. So it takes from 5 seconds to hundreds of seconds to predict the sign distance field. So this is one comparison with the classical Voronoi-based approach. In presence of noise, clearly they produce many spurious branches, while our approach is producing stable field, and hence skeleton extracted is stable for different noises. So this shows a result on different boundary sampling strategies. This result shows that we are the predicted sign distance field is insignificant to the type of sampling that you make. This shows a study done on the effect of number of boundary samples used for prediction. We are robust to the number of samples. Even at n equal to 128, you can see we produce coherent sign distance field. So this is an important ablation study that we did. This shows how ground truth supervision is helping us to predict the sign distance accurately. The first study is using the iconal optimizer with only boundary supervision. The second is supervision is provided only in a narrow band near the surface. You can see the quantitative matrices. Clearly, our approach has lowest SDF L1 error, chamfer distance, and the gradient field is close to 1 in our case. This shows the same qualitatively. The truncated SDF focuses on near surface accuracy. So you can see surface is reconstructed properly, but the interior field is not accurate. While when you use only iconal optimizer, the SDF prediction fails. So this is an ablation study done on the encoder architecture. Instead of using a local conditioning, we replace it with a global conditioning as done in the deep SDF architecture. But both quantitatively and qualitatively, it was observed that the result is not good. So this is what we get when we do only a global conditioning. This is another ablation study done on the activation and positional encoding. So clearly, Fourier encoding is required to preserve sharp features, but still we couldn't preserve all the sharp features. Yet removing the Fourier encoding increases the error and L1, chamfer, and Hausdorff. So this is again visualized qualitatively. So this is one failure case that we observed in presence of sharp corners. So the SDF prediction is smoothened out. Another failure case is in presence of very thin structure where the SDF prediction is inaccurate. So you can see here a thin needle kind structure where SDF prediction is inaccurate. In summary, we created generalized neural SDF for 2D point set with accurate interior SDF. Through experiments, we showed that full domain exact supervision overcomes the reliance on regularizers like iconal, and this generalizes to unseen shape without any test time optimization. It also supports robust medial axis extraction. It is stable under noise, outliers, and missing regions. In future, we aim to work at 3D by creating this data set based approach, and which will reduce the reliance on optimizers, thereby improving the training time and the inference time. Thank you.
Thank you so much for keeping time there. Very interesting work. Maybe you've got some questions. Well, I'd like to ask, what happens once a representative top so that we have a whole house? Would you all be able to recognize that?
Your question is how you represent shapes with holes
Yeah.
in the ground truth, in the training data.
Yes.
We couldn't do that in the future. Actually, we can do that in 3D. We have already done 3D work also. In the 3D, we created shapes with holes using B-spline surfaces. Are you asking that the ground?
Recognize the fact.
You could see this result, right? This the network is predicting this. The network is predicting the
Oh, yes.
yes. But we didn't have this in the training data.
Yeah.
But network predicted it accurately.
Nice.
Mm.
You got the microphone.
So I was with my about company time. So you say we are leading on the whole of it, therefore we will be fish. But I was wondering, so if I compare to let's say more additional euros different functions, they are praying for every new shape. They are retrained minutes. But here you need to have like not training, not person. How long is this first thing?
But the training is done only once, right? Yeah. Yeah. Yes. This training took close to 3 hours. Yeah, just that. Yeah.
And then it starts sections.
Yes.
What about the inference stuff?
Inference time is 0.18 seconds. Yeah, it's there. Yeah.
Nice.
Yeah.
I think this is curious. I'm wondering how short complex works where the new text goes like the words. How is these like do you recognize line or use string words? You have some use
Yeah, I think we have results. Corners, right? You're asking about sharp corners.
Right. Like those things. Yes.
where the video has goes down or
Yeah. But few corners get smoothened out. That is one limitation we observed. Like the professor who talked in the morning, we also face that difficulty. Maybe we'll have to find strategies to solve that issue. I think. Huh?
First, yeah.
Yeah, but that is captured, right? Okay. Thank you. Yeah.
You have questions?
He's asking from top.
Okay.
Thank you very much for this wonderful section. Actually, I just wondering, actually, I know that it is quite difficult to calculate and according to how many geometry you have in the and outside geometry. I mean that, and you show that, I mean, some geometry is people. And actually, and then that geometry, they found my increase the amount of the urine to be inside the and how affect your
Okay.
and algorithm. Given that when I try to more than 5 urine and that's I get the error and so
Okay.
it's quite
Hard, yeah, maybe. Yeah. Actually, we could have tested that. I think we do not have that complex inside outside whole cases, right? Maybe I'll go back and test that. Yeah. Yeah, yeah. 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 Thank you.
Thank you.
Thank you.
So the next paper uh, is the problem that we use for learning students.
It's not recording broadcast. Broadcast is here. Şunu Hi everyone. Thank you for today to coming to hear this section. I will present far from the boundary fields, a field design for the non-solids that are cut object into the unknown numbers of pieces. This kind of driving application is a brittle fraction, but the representation is general. So any task where a network must learn a segmented implicit solid can use it. My journey and our journey and exploration for this thing was starting from the brittle fracture in games. At that time, I worked as for a game company to just build such kind of the brittle fracture animation pipeline. So brittle fracture is an instantaneous, no plastic deformation. So think about the grass and also ceramic and also rock. Such kind of is existing routes to get such kind of shape sit at two extremes. First is the physical simulation. We give the realistic fracture surface, but it takes maybe 20 minutes to 5 hours to proceed. So also for the Voronoi prefecture pattern runs in the tenth of the second, but such kind of the shape are monotonous. So we want to both release and also the speed of the geometry generation. So we try to explore such kind of technique via the deep learning to learn the segmented implicit solids. That's that kind of the object we want a network to represent a solid broken into pieces. The fragment counts varies per example, and also the pieces are homogeneous. Uh, but unfortunately, there are no such kind of natural levels can do that. So the closest techniques in the computer vision is a kind of the levels and also masks we use in the image learning. So why can we borrow this kind of segmentation to these tasks? The answer is that levels assume a fixed and meaningful class set, but fracture gives a variable numbers of the interchangeable pieces. So a level targets an impulse. What we need is a continuous scalar field, and that field must satisfy three requirements. So first is that we need to just separate the arbitrary numbers of the homogeneous fragments. For second, the chain stability on the MLPs and also the neural implicits is needed. For third, round trip back to clean, leak free meshes is needed. So these three structure will structure the rest of the talk. So on the starting point, we just found a scientism field. The name called GSSDF, but we just think this is a simple scientism field with an external flip. So we give a new name, but actually it is totally same as the scientism field. So at every point, we stored such kind of distance to the nearest fragment boundary. Such kind of boundary becomes the zero shot. zero set, and the entire segmentation lies into the one continuous neighbor-free field. So with this representation, the requirement the first requirement is done, but there's still two problems remain. So when we actually chain on it, two problems appear. The first one is that the small fragment vanish. And also for the second, the MLP chaining is unstable. So to solve the problem one, a small fragment spans a tiny distance range. So the 0 to the 0.1 can just be the main of the part of the values, while a large one spans in the full range. Sampling and also regression barely sees the small values, so the small fragments simply disappeared. To this problem, the fixed solution is to renormalize each fragment to the full 0 to 1 range. So for the second problem, the interesting signal lies in the right on the boundaries, where the fields turns over sharply, but the uniform sampling expands the network's capacity on the flat interiors. The fixed solution is to just concentrate training samples near the boundaries, which is a common sense for the such kind of training technique. So putting both such kind of physics together with the FFBF, for each fragment to find such kind of point farthest from the boundary, deposit in the interior, and use its distance as the normalization reference. So look at the left part in the figure. Under the GSSF, the small fragment peaks well below 1. So it's a kind of value like 0.4 or something like that. But under the FFBF, both fragment peaks at exactly 1. So small pieces survive. So boundary also stay sharp. Chaining should be stable. So according to this design, the requirement first 1 and 2 can be satisfied in the same time. So on the continuous neural interfaces, the full recipe is that we use the MLP plus the boundary-centric sampling and also plus the FFBF normalization. So you can see that after the ingredient effects, for the a plain MLP on the GSS SDF, the boundary is blurry. So after we use the B, the ones that adding the such kind of the boundary resampling, it will become better. So after C, by adding the such kind of the FFBF normalization, the fragment separation becomes crisp. And also, there are two findings we can find in such kind of the chaining curves. First is that for the if we use a FFBF, the convergence will be faster than according to the random results. Instead of fewer inputs than the UDF and also chunked UDF or the GSSDF. So, and also second, just as useful in practice, because every fragment occupies the full normalized range from zero, maybe -1 to 1. So the loss value becomes a reliable indicator for whether the field is actually being learned or not. So with the baseline, a lower loss can just hide such kind of the fragments that were never captured. The loss looks good while small pieces are silently missing with the FFBF. If the loss is down, the fragment should be there. And this is also the method we use for the reconstruction. So the flooding will just go to the step by step to just make the value from the 0 to the 0.01 and then gradually just change the threshold. After that, each kind of the part will be separated by with this kind of the procedure. So after the procedure above, the requirements 3 would be done. So back to our meshes, we compared against UDF-based extraction pipelines, such kind of the CAP UDF, also mesh UDF. and also the NDC. The top row looks plausible for the outside, but look at the interior cuts on the both bottom row. The UDF, the pipelines leave the noises and also shatter interiors. FFBF with the simple flooding algorithm will recover clean, also watertight fragments. And with a small exploration of that, you can see that the fracture pattern will closely match the BEM reference on the right part. But actually, since the capital UDF, also mesh UDF, also NDC, it's kind of the single phase, single material extraction. So the comparison is unfair. But actually, you can see if you use a try to choose such kind of multiple extraction, there are few techniques we can use. So the flooding with the such kind of FFBF should be reasonable. And also to quantify it, we use we call it MFCD, which means the multiple fragment transfer distance. Since there are few such kind of the measure tool, we just design our version. So the transfer distance computed per fragment. So a method that jumps small pieces is parametric. The number we can see the GSSDF collapsed to the 12 fragments against a ground truth of the maybe 48 FFBF recover from the 47. The small pieces are back, and the cost such kind of the FCD from the 0.38 down to the 0.06, with the one weight scores improving similarly. And also, we do this corrected comparison. Such kind of experiment before is depends on the maybe 50 case data set. So for the such kind of this kind of experience, we use a 50 case data set. The loss also random result will be converged in the end for all of the such kind of representation. But in the case we use a full data set, which in the existing paper with the 500 data sets to train, the difference become more obvious. So GSS SDF with the maybe 500 case data sets are noisy and also broken. Once we use the FFBF, the BDF, and also the MLB, and also the boundary sampling with the 500 different cases, we required coherent fragments close to the ground truth on both the square wave and also the Bernie model. So also the FFBF is not such kind of the a fracture specific representation. It is a numbing target for any solid dividing to the homogeneous region of the unknown cards. A runtime destruction in games and VR can work. Also, the multi-region autonomy in the biomedical shapes. Also, the cell segmentation can use it. Use it. And also for green structure forms, and also CAD part decomposition, also in the 3D printing in different material may use it, but we have to test a little, but actually not so far away. So the one takeaway for such kind of recipe is that for reputation, we can use a FFBF, which means the per fragment far from boundary normalization. So for training a plain MLP with the boundary resampling, and also you can just a faster conversion and get a loss that you can just actually trust. For reconstruction, use the flooding. Also, we can just get such kind of watertight fragments. So one level 3 continuous fields for such kind of arbitrary numbers of the homogeneous pieces can just earn from this kind of practice. So there's still such kind of limitation here. So first is the per object chaining, there's lack such kind of the generalization. And also there is no fully real time at the high resolution, something like the 256 resolution. And also for such kind of solution, we need to just develop such kind of continuous representation between the multiple segmented implicit patterns. So we can just try to just develop such kind of representation. And also need to some speed up also needed for this in the future work. So to summary, the FFPF is a simple idea, just try to just normalize by the such kind of farthest from the boundary point, and that will just turns otherwise ill points segmented implicit target into something a network can just know. So small fragments will be preserved and also fast and also transversely chaining multiplying mesh can just recover. Thank you for to hear this such kind of presentation, and I'm very happy to receive such kind of question.
Thank you very much. Very impressive results. The main result of some questions.
Mhm. Oh, yeah. So the output we just design such kind of representation as output. So for the other pipeline we try to do is a kind of we use a such kind of the vector as our input. So it's kind of the conditional vector as input, and also the output should be such kind of the segmented representation. Yes. Yes. That should be a question that I just do such kind of the habilitation study. But actually, what we found is that all of the such kind of the activation functions work. So there seems few difference. According to the paper, we just tried to do the ablation study, and CLU and also the serial is worked.
Any more questions? I have one. I noticed that your segmentations, the final result was one color. Have you looked at texturing and what happens when you try and texture?
Yes. Yeah, and that should be the lack of this paper, but actually I think it can be used for maybe different technique to just do the modern geometry, but also the texture. But we still fail to just do the extension external work for this to just including the texture. I think it will be done in the future.
Yeah, they definitely.
Yeah.
I have picked on that.
Oh, please allow me to take a reference.
Well, thank you very much.
Yeah.
And yeah, yes, as well in the past. And one thing about this one, when you see your previous stall as well,
Good. Thank you for the presentation. Yeah, actually, those are my supervisors, and I guess that Eric Gallin was your student at some point. So quite funny to be there. All right, so I will now present you our paper, Extreme Continuous Level of Detail for Skeleton-Based Implicit Surfaces. As you all know, implicit surfaces, I guess, let me just quickly recap the motivation. Those are really nice this is a really nice formalism to represent surfaces. It enables really a strong editability of those surfaces as well as really precise small details. Yeah, however, those are not free to compute. For instance, the dinosaur that you can see here is made of more than 200 bones, And to compute implicit surfaces, you need to process the implicit function lots and lots at lots of time. So for each point, you need to compute lots of computation and everything. So it's quite long. That's where our approach comes in, to introduce level of detail to simplify the shape, smoothing out, to enhance the computation capability of 3D scenes using implicit surfaces. So our approach achieve between 1 or 2 order of speedups in the rendering time for various types of models, as well as reducing the aliasing of the smoothed out surfaces. And we are currently the only level of detail approach that is enabling topological changes in the surface to really go to the extreme simplification, such that everything becomes an ellipse at some point. When everything is only 1 pixel wide, you don't really care of details anymore. So obviously, level of detail is not new in the study, and it has been implemented for implicit surfaces a long time ago. For instance, in the case of blob surfaces, we already have method to compute level of detail. However, the transition between the details as well as the generation of the actual surfaces are not yet automated for the blob surfaces. Later on, we've introduced normal warping that adds back the details on the smoothed surfaces, taking care of the transition, because if you don't really see the transition, there's no need of transition anymore. However, still the level of detail needed to be computed by hand, so that's quite tiring. Closer to our concern on skeleton-based implicit surfaces, there's absolutely no traditional approach to simplify the skeleton. However, there's what we can say reversed approach that we try to adapt detailed on an already smooth surface, like the work of Cedric Zani, for instance, that will add a small patch of details on the overall surface to create some cracks and nice features on the surface, as well as the one of Angelidis that subdivides recursively the skeleton to smooth out even more the surface as the camera goes closer to the object. All right, so that is absolutely the opposite of what I will be presenting now, because what we are trying to do is to get out of the surface. Quick recap about the underlying mass of implicit surfaces. So those are potential that are being integrated over a skeleton. So the skeleton represents really like the idea of the shape, and the integration will inflate it and create the smooth surface in the end. Quick recap. Implicit surfaces are defined as a level set of a continuous function, and usually you are quite free to use whatever function you want. Simplest of all being the blobs. It's quite an old model, and it's quite nice for its parameterization, because you have radius control over all the primitives that are themselves being represented as distances to some skeleton, either point, segment, or triangle, or whatever you want. And those distances are then, and that's usually forgotten, are then converted as a potential, giving a new degree of freedom in the resulting shape, because to convert this distance, we use kernel, and those kernel are being parameterized by a width. That will be important later down the line. And finally, the last parameter that is always being forgotten because it's always being put at 1.5 is the ISO level, targeted ISO level. For this, our method, we choose to actually alter this ISO level, targeted ISO level, so it's good to have in mind that we can actually play with the entire set of parameters and not only the radiuses and the points. All right, so that was for the blobs. Unfortunately, they suffer from the bulk effect, meaning that when you have lots of blobs near one each other, their potential will sum up, creating some bulks that are highly undesirable. To palliate that, we can integrate the potential over the entire skeleton, which take care of the smooth blending of surfaces. However, By doing that, you also integrate the radiuses along the skeleton, losing out the control that you had previously on those radiuses. And finally, so to palliate this last issue, we, for this paper, are using the scaleless convolution surfaces that normalize everything depending on the radiuses and enabling very sharp details on very smooth and wide surfaces. However, this is not free, as both the number of primitives and the complexity of those primitives do create some computation time and slow down the process. So that's the goal of our approach, to decrease the number of primitives as well as their complexity. All right. So now will be the overview of our methods. The main diapositive that you want to memorize is this one. We start with a simple shape that we want to simplify to speed up everything. Our pipeline works as follows. That's a three-step framework that starts by inflating the shape to smooth out the details, change the topology, and basically simplify everything. Then, because this is not accelerating anything, just inflating it, we remove some useless bones to actually speed up the process. And to keep everything nice and tidy, we correct the inflation, but through the mean of a deflation on specific axes. And if everything is done nice and well, the resulting shapes should be really close to the pruned shape, as you can see. All right. And finally, because we want to achieve nice runtime timing, actually, our pipeline is fully pre-computed to really just care about the rendering during the rendering process, meaning that both the inflation, the pruning, and the deflation are being parameterized through a single level of detail parameter that we call lambda, and that it goes from 1 to draw the original fully detailed shape to 0, which will draw an ellipse, roughly, because in the end, everything is elliptical. All right, now for the details. The inflation is being performed by both jointly decreasing the targeted ISO value that is usually forgotten and increasing the kernel width of the kernels. This has the effect of inflating the shape at the expense of increasing the volume and losing the aspect ratio, as we'll see later, but that's for the deflation step. This is the simplest of all. Then we want to actually simplify the skeleton to speed up the process of computing the shape. To do that, we introduced a dynamic skeleton that will evolve during the variation of lambda, meaning that for a level of detail parameter, a given one, we know which drone to compute and to process, and which drone to erase and to discard. And to compute those, we iterate over 3 operations, namely the deletion. If at some point during the inflation process, a primitive becomes negligible compared to another one, we allow ourselves to just remove it and avoid it. Then the merging operation, the collapsing operation, if at some point a primitive really look like a point because it's being so inflated that it's really spherical, we allow ourselves to remove this primitive and replace it with the corresponding point. And finally, if 2 points are really close to each other, once being inflated, then also we allow ourselves to remove those 2 points and replace them by a well-chosen single point. In both 3 cases, we either decrease the number of primitives or the complexity of the integration of the potential. So we reduce the computation in each cases. However, the inflation does alter the volume and the aspect ratio of the shape. As you can see here, the ellipse under a uniform inflation turns out into a sphere. So that's not what we want, and to palliate this, we introduced the level of detailed axes as well as anchor points. So those 2 notions, the level of detailed axes are simply the principal axis by default of our shape. This can be tuned manually if the artist wants it, but by default, we decided to say, oh, let's get the shape, an intuition of the shape by using the principal axis. And the anchor points are simply the intersection between the shape and those axes, meaning that in the and we want to keep those constant in space during the entire process. So originally, those anchor points are being defined by the original surface, and as the surface will inflate itself, we will downscale, we will compress this inflated shape along those three axes to keep the anchor point fixed in space and preserve the overall aspect ratio and volume of the shape. All right, so I will let you admire our smooth transition of shapes. As you can see, we are able to consistently smooth out the shape in a natural behavior. The topology may change, as for instance, the Scorpio passed from a sphere-like topology to the donut one with a hole when the antenna link with the tail, and go back to the sphere one when it become a simple ellipse. We are able to achieve between 1 or 2 order of magnitude of speedups for the most simplest level of detail, smoothing out the surface and reducing the bones. And during the smoothing out of the surface, we also reduce the aliasing because less detailed surface is less susceptible to aliasing artifacts. We consistently decrease this aliasing features, not features, problem issue in all of our test phase, and especially for the dinosaurs one, we are able to half the aliasing. All right. So to recap, we are the first level of detail approach on convolution-based implicit surfaces, achieving between 1 or 2 order of magnitude in the speedup of the rendering time, while decreasing the aliasing. And furthermore, we are able to really simplify to the extreme the shape by enabling ourselves some topological changes. However, there are some limitations, the main one being that because we're inflating the bones, we are currently not compatible with bounding volume acceleration techniques because those suppose that the volume stay fixed in space. So this is the main limitation, and as a future work, we may think of some acceleration, inflating bounding volume hierarchy-like structures that will be able to match the inflation pace of our surfaces to speed up even more the processing of those. And furthermore, as everything is being pre-computed, we are currently not able to animate the resulting level of detailed shapes. For that, the only piece that we can think of is to have some robotic animation, meaning like we will compute the level of detail of the arm and only animate the arm uh, only like separated parts. All right, thank you for your attention, and I will now be glad to take your question.
Well, it was lovely talk. I do remember talking to Eric about level of detail many, many years ago, but we never did anything about it. So
Yeah,
it's great to see people have done this work. So I'm going to jump into my question first. This is something. And one of the things that was interested in then and now is the relationship, the distance and length. So if you've got a linear relationship when you're moving the camera, does that work? And you have very good results when you just use the linear relationship.
yeah, actually, we are using a linear relationship, meaning that we have a threshold between at which point we will start the level of detail simplification and an ending threshold at which we will end it. Otherwise, if we really, for instance, if the lambda parameter goes to 0, everything explodes for division by 0. So we stop it at some point. And for now, it's really just a linear relationship. We sort of actually doing some evaluation of the area of the shape appear on the camera to try to minimize the aliasing, for instance, to try to optimize and better link the level of detail parameter to the distance to the camera, but it did not went anywhere. So that's for future research as well. But we thought of it, and for now it's just a linear relationship.
Okay, thank you. Can we continue to number? Yes. I have a question. That is news or communication, right?
Yes.
And then if you were to have this type of moving path, is it a far step to try to get this to run on the real time for animated systems, or is it not possible?
The difficulty is that our pre-computation is in n square, no, not square, cube towards the number of bones. So if you have a really simple model, it can work. But on those models, it takes roughly like 30 seconds on an average CPU to process. So it's not run real time anymore.
What made me explain that you have these different rendering algorithm shop. Let's see possible more complex. This was the motivation of doing this. I was wondering when you simplify the maybe the end shape is so simple that you don't need the more complex rendering algorithms. Did you consider also during simplification swapping the random use case only for very high level of data?
Actually, we did not consider that. That's actually a good direction for future work, especially because at some point, and we can actually measure it, everything turns into an ellipse. And when you have a crowd simulation, there's actually a lot of elliptic. So that's definitely a good future work aspect for future research. But yet, we did not thought of that.
Any other questions? Okay, well, this is a big speaker again. From your really
Okay.
learning improves skills and communicates new knowledge.
So good afternoon, everyone. I'm Binsi again from IIT Madras, and my advisor is Professor Ramanathan Muthuganapati. So the previous talk was on 2D point sets. This noisy 2D point set. This is on noisy 2D images. So before I start, I explain what a skeleton is. Here our input is a 2D shape represented as binary image, where skeleton or the medial axis is a thin center line abstraction of the shape, which is topologically and homotopically correct. By topology correctness, we mean the resultant skeleton should be connected and it should capture all the junctions. By homotopy preservation, we mean it should capture all the holes. It should, if the shape has a hole, the resulting skeleton should have a loop around it. The core problem with the medial axis or the skeleton is its sensitivity under noise. Small perturbations on the boundary can create a lot of insignificant branches like this. So this represents a clean shape with a clean skeleton. This represents a boundary which is perturbed with noise. and this is the resulting skeleton. So this makes the skeleton unuseful. The usual approach in the literature is to assign some significant measure to the resulting skeleton after you extract the skeleton. So this is a significant measure called the vanishing angle. After you establish this significant measure, you have to prune at some threshold to get this clean skeleton. But the issue with this kind of thresholding is this requires manual intervention, because if you use the same 50-degree threshold for this flower shape, you lose many of the important features. So calling it appropriate threshold for this shape is 45-degree. So this calls for manual intervention. So these are different significant measures in the literature. Each of them has its own pitfalls. Some of them do not completely remove all the unnecessary branches, while others do over prune. So in the literature, there are few approaches for actually one approach for learning skeletons in a supervised manner. So this was one dataset that was released as part of a CVPR challenge, but this is no more publicly available. And also it is not suitable for a pruning task because you can see many unpruned branches still exist in the dataset. So our motivation was to go from a noisy shape, directly to a pruned skeleton by learning it. So we already had one paper in SIGGRAPH Asia as technical communication last year, where we were trying to go from a noisy shape to clean skeleton, so called ConfVSNet, but it had junction breaks. So that to avoid this topology break, we are proposing a topology aware junction preservation loss. The major contributions of this work are, since skeletonization is used in graphics and interactive application, we are focusing on improving the inference time of our skeletonization approach compared to the previous work, and hence we create a compact model which is 1,000 times smaller than a teacher model. We distill from a base 64 unit, which is called the teacher model, to a base 2 student, which is called the student model. The student model now has accuracy as close as the teacher with 1,000 times fewer parameter and being 6 times faster than the teacher. And since there is no common evaluation benchmark for evaluating the skeletonization problem, we created a human annotated noisy shape clean skeleton benchmark. So this is the data creation process. We use spline curves to create various geometric shapes, and then we rasterize them at high quality so that we get clean medial axis. So this is done under expert supervision. So this entire process shows data creation for one sample. After this, we add controlled noise to the boundary. This is also done under expert supervision because adding noise shouldn't add a new feature, so thereby bringing in a new medial axis branch. Hence, after we add controlled noise, we maintain the skeleton of the original clean shape. So this gives us an appropriate data set of noisy shape, clean skeleton pairs. So this is the architecture of the teacher-student network. The teacher is a base 64 unit from which we distill a base 2 student. Now, at all these levels, we transfer knowledge from each of the layers of the teacher to the student. This is feature distillation. And now at the output, using the KL divergence loss, we transfer the soft labels of the teacher to the student. And also, to preserve the topology, we propose the junction preservation loss. So as I mentioned, we go from a base 64 teacher to a base 2 student. You cannot directly go, so there will not be stable knowledge transfer if you directly transfer from the base 64 teacher to the base 2 student. Therefore, we use intermediate teachers and do a sequential knowledge transfer. So this is why a junction preservation loss is important. This figure shows that we have shown T, Y, X, and plus junction. You can see these red pixels show the removed pixels. In this case, we have lost 3 pixels from the endpoints. Same 3 number of pixels are lost from the junctions. But for skeletonization, this is more catastrophic. Losing 3 pixels from the junction leaves a skeleton, leaves a structure disconnected. So this is more catastrophic than this, but only by binary cross entropy laws, if you take, will treat them equally. They will consider them as 3 missing pixels. So to detect missing pixels, so we propose this loss, which is able to detect missing branches and spurious branches. So you can see this. The same tip, when shortened, the binary cross entropy loss is not able to, or the dice loss is not able to capture that in loss, while the junction loss is able to capture that. So this is the entire loss on which we train the network. So total loss consists of the distillation loss and the task loss. Task loss is now a combination of BC, dice, focal, along with the proposed junction preservation loss. And during distillation, we do transfer the features at all levels and also the output soft labels. So this is the process of creation of the evaluation dataset. We collected noisy shape from 7 shape benchmarks. Then we create, using distance transform, we created the skeleton. So of course the shape is noisy and the resulting skeleton has noisy branches. Then 5 annotators manually clean the skeletal branches to create a clean skeleton. After which we reconstructed them to ensure that this skeleton has all the significant branches to reconstruct the shape. So this serves as the evaluation dataset. So these are results on the evaluation dataset. So the first row shows the result of the classical medial axis. So these are results on complex junctions and even shapes with holes. This shows the noise robustness of our result across different noise levels. You can see our approach at the bottom is able to produce the same stable skeleton. So while the medial axis produces insignificant branches. So we compare with different learning based approaches. So all the large foundation models and the big networks overfit on a small skeleton dataset like ours, while the small networks like mobile net, efficient net, squeeze net, etc., do not accurately predict skeleton also. This is the conf-PS net that our prior work, which had small junction breaks, and the last column shows our result. So the major problem with the large network is since they overfit, when they are given new shape, they do not generalize proper. So this result shows how a distilled model performs in comparison to a scratch model. When you take a base to scratch model, you can see the prediction is fragmented and noisy, while the distilled model has good predictions. This is a quantitative comparison with the classical approaches. All the classical approaches are geometry based, and hence you can see that computation time. Uh, it may be noted that they run on CPU while we run on GPU. We require only 0.56 milliseconds. So while the teacher takes 3.52 milliseconds, the student takes only 0.56 milliseconds to predict the skeleton. So these are qualitative results. As I already mentioned, geometric approaches call for a manual intervention. So this is quantitative comparison with all the learning based approaches. So you can see the average effort score for a base 64 teacher is 0.697, while that for a student is now 0.693, showing that we have effectively distilled the knowledge from the teacher to the student. And look at the inference time. The teacher takes 3.52 milliseconds, while the student only takes 0.56 milliseconds. And these are the results. Of course, large model takes more time than even the teacher unit. So this is again the same plot. You can see we have the least inference time and good uh, F1 score. So this is a ablation study done on the different configurations and also on the distillation configuration. We distill on the distillation weight and also the temperature. An important thing to note is that removing the junction preservation logs result in a dropping of F1 score from 0.762 to 0.55, showing that the F1 score is indeed contributing to the accuracy. So this shows how distilled model wins over scratch model over all levels. So this shows base 64. This is base 32. You can see at all levels, distilled model is performing better than the corresponding scratch model. So during experimentation, it was observed that a weighted binary cross entropy loss is required to efficiently transfer knowledge. So with classical binary cross entropy, when the FN score is only 0.587. So showing that for an architecture of this kind, where you want to do a distillation of almost 1,000 times, a compression of almost 1,000 times, there were two design strategies that we observed. One was using this weighted binary cross entropy, and other was the batch normalization. So these two, although might seem like two small things that we do in deep learning, but contributed a lot to our result actually. So this figure shows that the resultant skeleton is preserving all the important shape features. This is shown through reconstruction. So this is one failure case in presence of high ligature regions. For example, you can see a junction break here. So this is one failure case we observed. In summary, we created a distilled base 2 student model from a base 64 model. The student model is only now 31K parameter, and this 1,000 times smaller than the teacher, and while being 6 times faster with comparable FN score. The junction preservation loss ensures topological correctness. We could observe that large and foundation models overfit on small data set like ours, and we have created practical and real-time skeletonization strategy for interactive and edge deployment. Thank you.
It's maybe we certainly have time for one or two questions. So I was very impressed with the how far the neural nets have come to actually give you these kinds of results. And I did notice that you compared to a large number of other models.
Yes, yes.
So in doing that, did you learn anything from looking at these other models? What was how did you know that this approach was going to be better than they were when you started?
Yeah, honestly, I didn't know that the small networks are going to be this capable. Uh, but one thing was that we started with the whatever compute we had in our lab. We wanted to show that geometry problems could be solved using the learning, but that is democratized for whatever computing resource that we have. So we did compare with large models, and we found that results are not very good. And then, yeah, that was a promising place. Then we thought of design strategies. So then we could learn more about improving the networks using small architectural changes. So we focused more on smaller architectural nuances, which could actually do a lot of improvements to the result than just picking the model, giving all the data and looking at the result. We worked on the architecture because we were forced to work because that was we had limitations on the computation side.
Well, it's impressive to me that machine learning has come so far. Thank you very much. Maybe there's small questions from everybody's very keen to get to the right. So, okay, I'd like to thank all the students in this session.
Okay, nice. Hi everyone. Welcome back. Our next it is our uh, is actually improve the content analysis as well as descriptions. We have including stickers. The first one is implicit European the problems and on access. How well presented.
Yeah. Hi everyone. So I am Nirot Palitta. So I'm a postdoc at University of Manchester Digital Manufacturing Lab. So I'll be presenting our CAD paper called Neural Field-Based Process Planning for Multi-Access Manufacturing, direct control over collision avoidance and toolpath geometry. So this was done along with my colleagues Jianyu Tao, Yongshu, and my supervisor, Professor Charlie. at Digital Manufacturing Lab in the University of Manchester. Yeah, so let's start. So before I start, so just a brief introduction of what the multi-axis in the title means. So this is a type of manufacturing, and so we have different sorts of manufacturing based on how the tool moves. So the first we term as 2.5 axis, in which the tool just moves in along the two translational axis and incrementally along the third translational axis. So something like the conventional 3D printers are designed to move along 2.5 axis motion. Then we have 3 axis in which the tool can move continuously along 3 translational axis. The image shown here of the Delta printer is commercially built for 2.5 axis, but because it has large clearance at the near the nozzle, so we can kind of adopt it to 3 axis. And then we have multi-axis, in which like it's generally classified as more than 3 axis, depending on what kind of manufacturing you're using, in which the tool can translate along 3 axis as well as rotate along 2 or more different axial directions. So just an illustration of how it may look like. So we have shown a robotic setup that can do more than 3 axis of motion for the tool. Again, so this is the axis here means the axis of the tool, not the setup itself, because the let's say the robotic setup shown here has more than 5 axis, so it is 8 axis robot, but the tool motion is itself like 5 axis. So why do we need multi-axis? So I'll be showing some examples from the case of additive manufacturing, but we can have similar benefits for the case of subtractive manufacturing as well. So a few years ago, this paper from SIGGRAPH, they showed that using multi-axis motion, we can remove support material for different cases of FDM, which is a type of 3D printing. But very recently, there have been more functional improvements in the application wise. So this paper showed that uh, we can increase the strength of the parts by adopting by moving into higher axis of motion, because we no longer then need to be like in a planar domain, so we can deposit material in a curved way. And this is especially important if we want to like put in more anisotropic materials or more functional materials like continuous carbon fiber, where we can align. This allows us to align the carbon fiber along the stress directions, because according like the properties of those material are quite anisotropic, so they have higher strength, higher better function along the axial directions, and not so great along the other directions. So it helps us to align them along the stress field. But what are the challenges? Like conventional 3D printer, like when we do 2.5 axis motion, the tool almost remains above the printed substrate, so which means that there is less chances of collision with the part itself. But when you move into like the higher non-planar motion, there are increased chances of collision. And when this paper was published, the current methods did not control the collision directly. And also we have seen that there is a disconnect between the layer generation and the paths generation itself. So they are two subsequent different processes. They are not optimized together. And also the geometry of the structure itself is indirectly controlled. Let's say if the curvature is controlled through Laplacian, which is not a direct control over the curvature, and then most of the processes are mesh dependent, then it depends on the quality of the mesh that we have, and also as a result are not very differentiable. So in our case, we propose to have an implicit field representation. And why we use implicit field representation is like there are many reasons. One is that we could evaluate the field at any point uh, in a very short time without needing for any interpolation, and also we can easily compute derivatives. So for our case, we use a sinusoidally activated neural network as an approximator for a function, so which is used to represent the fields that we have. So for each coordinate, we output a field value, scalar field value, and then because the function itself, like the network itself, is differentiable, and especially because we use sinusoidal activation, so it can be differentiated any number of times. So we can easily compute the derivatives at any point. So we can compute the first order derivative, special derivative, which is the gradient, the second order derivative, the Hessian. So the pipeline is we start with a computational domain, which is also represented as a signed distance field. Then we compute two different fields, which are called the FL, the layer field, and FP, the path field. And we can compute the isosurfaces of those fields, the LL and LP. Then we can take an intersection. So the intersection of the two fields represent the path along which the, let's say, the carbon fiber or any path like along which the tool moves. So we have the layers, the isosurfaces of the first field, and then the tool path, which is the isosurfaces, like the intersection of both the isosurfaces. So the manufacturing or other constraints can be computed using the field values and their derivatives. And we define different loss functions, which I'll explain shortly. And then we can define a combined loss. And the objective of the whole pipeline is to minimize the loss. And once we reach a satisfiable value, we can use those functions to represent manufacturable fields with desired properties. So in our case, we have three different classes of loss functions: the regularization loss that controls the geometry of the layers and the path. We have the functional loss, which can control things like support free or layer or path direction alignments when we want to align, let's say, carbon fiber along stress field. And then we have the collision loss. And our collision loss is the direct collision loss, which I'll again show how it works. So how does a collision loss work? So let's say we are printing something, and then we have a layer which was already printed, which is C minus delta, the ISO number. The current layer is C, and then the future layer is C plus delta. If we place the tool at the current point, you can see two different points on the tool, Y2 and Y1. The Y2 lies on a future layer, which means that there is no material there yet, and there is no interference with the tool, and this is fine. But the point Y1 lies on a layer which has been already printed, which means that this is causing a collision with the tool itself. So we don't want that. So simply we can put a condition that any point on the tool should have a scalar value more than the scalar value at the tip of the tool. And because we have an implicit field representation, we can easily compute the field value at any point. Hence, once we assign this constraint, we can easily come out of the collision zone. And this can be easily posed as a loss function. And here, if you see the loss x both on the scalar field as well as on the normal, the orientation of the tool through the points. Next, I'll shortly explain how we control the geometry of different layers, because we can compute the derivatives easily because of our representation. We can compute the tangential directions, the normal of the fields, and as a result, we can also compute exact measures of curvatures and geodesic curvatures for a path. Here are two examples of how we control the layer curvature and the geodesic curvature of the path using loss functions. Similarly, using similar derivatives, we can impose functional requirements such as support free, where we impose a constraint on the orientation of the tool with respect to the surface normals of the part that we are printing. Or if we want, let's say our toolpath direction is T, and then we have an input field direction field D, and we want to align the toolpath along that direction. So we could simply say that the cross product of the two vectors should be 0 at every point, which means that they should be parallel. And then we can generate similar loss functions for that. Here I'll show an example of our application where we show how we print the fertility model with support and collision-free constraints. And this is the actual printing result that we do. And this is directly out of our neural, like the optimization network. We do not do any post-processing to avoid collision. And as you will shortly see, we can avoid collision directly without needing any post-check. And we can be sure that it won't collide because the collision was directly included during the optimization framework. And just quickly compared to the previous methods, our method generated collision-free layers without sacrificing any of the other functional requirements. Whereas for the other works, like through indirect control of collision, if we want to remove collision, it sacrifices the functional requirement. Again, so when we generated the loss function, so we put a we showed in condition for the additive manufacturing task, but we can easily make it convert it into a general collision avoidance constraint and apply it to other layer-based manufacturing processes like CNC milling or rough milling, for example. So here I show an example where the initial layers for rough milling lead to collision with the tool, but our using our constraint, general constraint, we can it automatically generates layers which are collision free. And here is an example. Again, this is directly out of the result without any post processing for collision checks. And the tool can go into the cavity without touching any of those boundaries. Yeah. So next, coming to the other stage where we come, so an application of how we can do tool layer path co-optimization. Here is an example of a S-shaped break structure, and we have a field which is conformal to the top and the bottom layers boundaries. So if we want to, if we use a like like what previous methods did, if we generate the layers first, we end up getting something like vertical planar layers, which match the tangent surface, which match the tangent of those direction field. And then later, if we want to generate toolpath on that, as what was done in a sequential process, we get a toolpath for the fibers. And as you can see here, although the fibers, the toolpaths match the direction field very nicely, but there is some amount of curvature. And so are curvatures generally okay in the paths? Yes, for some material, but for something like carbon fiber, this result shows that as we increase the curvature of the fiber deposition, the frequency of the error or the deformation in the fiber increases, which leads to sacrifice of the structural properties of the fibers. And also, it's very difficult to have high curvature during printing. It's quite not manufacturable. But in our current case, if we increase the weight of the curvature loss, we end up getting reducing the curvature, but as a result, we also sacrifice the direction alignment of the fibers. Differently, if we use our method for layer and path co-optimization, because the layer stage and the toolpath level stage can communicate, we end up getting results which leads to reduction in both curvature as well as better satisfaction of the toolpath alignment. So here is an example of a real example of application of our toolpath based frame optimization. Here we have a bracket, we apply a load and we get the maximal principal stress directions, and our objective is to align those carbon fiber path along those directions. In the same time, also optimize the layers. So here you can see both the layers and the tool paths. The black are the curves are the tool paths are optimized together. One of the benefits of our using an implicit method is that we can also add other functions, like here we saw an example of optimizing the setup together with the the toolpath and the layers itself. And again, here is an example of how we print the long continuous carbon fibers on the layer. And yeah, so we use the same robotic setup with two different deposition. So here we print the base material and then the other nozzle prints the continuous carbon fiber. And compared to the, again, the other methods, like the previous baseline method, which showed that it could achieve high strength, our method has less disconnected patches, more continuity, and also, as you can see from the graph here, the deviation in the angle with the input field is less. And as a result, when we did the test, we found that the red curve is our method, the blue is the baseline method of the high density carbon fiber deposition. So in spite of using 18% less carbon fiber, we had significantly higher stiffness and a bit higher breaking force. And this shows clear fracture in the fibers. Again, this means that the fibers were clearly aligned along the stress field. So we also did test on different applications, direction and layer, direction alignment and collision free for the layers, support and collision free, and also milling, which showed the universal application of our pipeline. A step further, so I said that we use sinusoidally activated neural networks. So this is like the function of like functional representation of the network, where we have a sine activation with a frequency term. And this frequency term can be really used to control how much information the network can express. But uh, there has been a lot of work around this area, because this is also a kind of a problem, because controlling, we don't really know how we don't really understand how the frequency term affects our different manufacturability or different representations. Um, so there has been like different works that worked on some sort of says taming the high frequency noises in the network. So in our case, we did a analytical study of how different frequencies affect different functional results of our output. And I'll not go into details. So this is like we figured out some good frequency terms directly from the shape of the size of the part itself. And then some other terms, like we said that we control the frequency, the curvature of the path, but we sometimes also need singularity in the paths. And near the singular zones, the measure of curvature is not great. So we use some sort of curvature filtering, again, more details in our paper. And then uh, we also improve some of the loss function definitions so that the convergence is more stable. So as a conclusion, we generated a universal implicit scalar field optimization framework that enables direct control for both layer and toolpath generation in different multi-axis manufacturing applications. So we also formulated a explicit collision avoidance for field-based optimization, and then we showed how different loss functions can be used for joint optimization between layers and toolpath, and clearly this has several benefits. One of them I showed, and then we went into a bit of analytical study of how the expression of those functions can be controlled to control singularities and the regularization for the field itself, so that we don't really have completely rely on the loss functions. We could inherently condition the network or the function itself to express some of the required structures. So moving a step forward, so some of the applications that we showed here used robots or little bit expensive devices, but then we tried it on commercial, like cheap printers. So on the top we saw a Delta printer, and bottom we saw the quite popular bamboo printer. And despite having very less clearance and only slight 3-axis motion for those printers, on the graph we can see that compared to planar printing, it still leads to significant improvement, and there is huge potential if the manufacturers start providing a bit more clearance, and hopefully they will do in the future. And also in our current study, in the paper that I just explained, we did not include any simulation in the loop, but our method, being differentiable, can easily be combined with one of the recent works from few of our colleagues, and this will lead to a whole complete pipeline of simulation in the loop, where we optimize both the design and the toolpaths together, along with everything like collision avoidance and all the manufacturability constraints. So speaking about limitations, there are a lot. So the first is we did not include support region during the optimization for collision. Then we did not include kinematics during our optimization, which is another scope. So as a result, our tool had to be, during the collision check, had to be symmetric, because we did not know how it would like align along the axial direction. Then our collision avoidance for the milling is too conservative, which leads to a bit of distortion in the path, which probably in the future we can solve. And then we only included a limited number of constraints in our current work, but then there is we can do a lot, like we can include path length, tool path length, or path like layer areas during the optimization, which can be easily done because we have a implicit formulation and we can compute those values easily. Yeah, those are some of the limitations that we have. And like, if you would like to know more, I can discuss after the session. Also, I have brought a few parts if you'd like to see how they actually look like, the printed parts, and I have a few more tested parts. And that's all from me. Thank you so much. And we have our code and all the results open source. So one of this guy. Thank you.
My first talk so I can see him certain words like first we were so what are the relations?
Uh, there are multiple reasons. First is that the conventional printers print at like very low layered height because we wanted to test our parts. Like we had less time, so we increased the layer height to like several times. Like let's say the bamboo printers print at 0.2 millimeter height, we printed 0.6 millimeter height. Uh, we did not explicitly control the surface quality in our method, but I can show some of the results where we have better surface quality because we use less layer height. Second is 0.8 millimeter. And we do not control we have not controlled the kinematics of the tool in this paper, which means that the robot motion is not smooth, which again can be optimized. And yeah, so these are a few of the answers. And like there is scope. So also we did not control how the material dynamics. So we did not control the extrusion rate and all of those things because for this work it was not relevant. But we have done some current works where we could improve the surface quality and reach better. But that needs more work, I think. Yes, there has been some works from our like co-authors which are working towards the trajectory optimization dynamics of the tool. Even Dr. Fang has recently published a paper where he optimizes the trajectory. I think it can be possible, and just because our pipeline is differentiable, we can easily make the whole kinematics kind of differentiable and put it as a modular setup where you can switch on and off different requirements. Uh, yeah, I think it can be done, and I do not see why it can't be. So possibly yes, because I mean, reducing the degrees of freedom would possibly increase the ease of control, but also I think it would reduce the generality of like the applications. So if you have a certain structure of a certain manufacturing process that you just want your device to be applied for and certain class of parts, I think you can definitely optimize your device for those applications with for better results.
So let's send some speak again. Well, the second secret is you will put the condition of small and students in the artists in isogeometric analysis or small and these slides or maybe non the comments. Yes.
Okay. Thank you for the introduction. So our paper is about simultaneous array adaptive isogeometric analysis using THP splines. And well, we didn't have up to now an introduction to isogeometric analysis in this conference, and nor I will make one. But briefly speaking, we want to use B-splines and splines in general in numerical simulation. So we regard the spline spaces, the spline basis functions as functions for finite elements, say. And in this context, there is a lot of developments and a lot of technology in order to do local H refinement. So to locally enrich the mesh, like the mesh you see here on the left. So you have a tensor product mesh, a tensor product grid, like the one we use for representing a parametric surface with interior nodes. And we would like to have some locally inserted nodes in these areas in order to enrich the space locally in the middle while keeping coarse basis functions around. There are a few technologies to do this, such as the T-splines, LR splines, and hierarchical B-splines. And the hierarchical B-splines is the ones I will use in this talk, but I will not introduce them at all. Because what I want to do in this talk is to actually consider another type of refinement, which is called R refinement, coming from the word relocation refinement, where essentially in the terminology of CAD, it would be reparametrization. So we can reparametrize a surface, and so we can compose it with another map and have a new parametrization. This implies contracting, say, the isoparametric line, so you have new elements, new subdivision that concentrate, as you see here, in the middle. So this is the R refinement. This is a relocation of the nodes, because in our finite element analysis, these are just nodes that will be used for the numerical simulation. And what I want to do now is to combine the two. So take the best traits of the both and present you an approach that we can locally H refine and R refine the mesh and see what that gives to us. So schematically, you have the R refinement. As I said, you start with this square domain. You reparametrize, so you do the R refinement step, and you get concentration of the nodes around the regions that are implied by your monitoring function. This monitor function is a function that tells you where you need to concentrate your nodes. On the other side here, you have the edge refinement. So you start with the same grid, but then you locally enrich the grid and you keep the map F fixed. So you arrive in such a situation. And what I want to do is to combine them both. So you do R refinement and then edge refinement, and you arrive to a mesh which is locally refined, and also the nodes in the mesh are relocated, so they are not they are not following the initial parameterization F. Okay. Okay, so that's the initial map in F. And this relocation refinement happens using this map, which is a Monge-Ampere mapping. We are going to use to solve it using solving an optimal transport problem. So we will compute an optimal transport in order to relocate the nodes, and then H refine additionally to locally refine the mesh and iterate. So just briefly introducing the optimal transport problem. We are given two densities. The initial density is R0, is essentially the unit function, and you have a target density rho1, which is the density that you want to have at your relocated mesh. And what you want to compute is actually this psi, which is this relocation map that takes you from rho0 to rho1 with minimal transport. That it means such that the cost of this map is counted by the amount of distance that each point traveled from your initial square to your final relocated position. And all this by maintaining the mass, so maintaining the integral of the density. So there is a well-established theory. We know that the result psi is actually a convex potential, and we know that to solve these equations, we arrive at this kind of equations where we have the determinant of the Jacobian and the Hessian multiplied by the density rho 1. So, long story short, I will skip several details, but finally what I want to arrive at is that this problem, finding this psi, reduces to solving this nonlinear Poisson problem. So you arrive at this Poisson equation where your convex potential phi is your unknown solution and its gradient is your relocation map. And in order to solve this, since it's a pure Neumann problem, you can use, it's nonlinear problem, we can use Picard iterations. It's simpler than Newton method, but the non-linearity is not so strong here and it works actually quite well. And since you have a pure Neumann problem, you also might need a mixed formulation to solve it. And moreover, there is a third problem, which is that when you actually enforce the Neumann conditions weakly, you might get not 100% accuracy in the boundary, because the weak imposition of Neumann conditions is never exact. So we get these problems on the boundary, meaning that the map does not is not transported directly on the same square, but there is an error on the boundary. Okay, with this, I can tell you about our first contribution in the present paper, which is to propose a projection method to solve this Monge-Ampère equation. So instead of going to a mixed formulation, instead we project at every step of the Picard iteration. We project the gradient of the potential, and we obtain a new spline function that we can evaluate for the next step. So all this solution is happening in the isogeometric sense, meaning that we use B-splines to solve this equation, we use tensor product B-splines to solve it, and we obtain the solution as a function in a spline space again. Then, in order to tackle this problem with discrepancy on the boundary, as a last step, we would project back the boundary control points on the unit square, on our original boundary, in order to preserve the exact boundary. And if you do that, this is what you get. You get that your final result can be, it's like we snap the control points back to the unit square, because that's always our domain. And in that case, we can recover the one-to-one mapping. And we could actually show with a small proof that when we do this boundary correction, the map remains a bijection. So we can still use this map to relocate the nodes without any problems in our Jacobian map. Okay. So we tried this approach and yes, I show you here some comparison. This is the error in the Monge-Ampère equation that you would get, and I'll show you some comparison between our approach, which is here, and the approach if you use a mixed formulation, which is what would you do in a classical finite element setting. And we can see that this is much more efficient, because when you do this mixed formulation, you double the number of degrees of freedom, so you double the size of your problem. Okay, so then up to here we have the relocated map, we have our adaptive mesh, but we want to use this to solve actually some PDE equation. And here comes our second contribution, which is to test this new approach in some solution of PDEs. And when we do that, we have actually several possibilities, we could do an initial R refinement so that we relocate the mesh close to our features, say, and then continue with a number of H refinements. We could do a number of H refinements and finally relocate then the mesh as a last step, or we could iteratively, simultaneously do RH and in the next iteration again RH, RH, meaning every time we relocate the nodes and we use some a posteriori error estimator to also point to H refinement. So we call these methods a priori reparametrization, simultaneous adaptive method, and a posteriori misalignment. So ARM, SUM, and AMA. And yes, here you can see some illustration of the two. So, okay, here you have pure R refinement, pure H refinement, and the combination of the two. What we can see that we gain the advantages of the R refinement. That means that our initial nodes are better following our monitoring function. And finally, by doing H refinement, we can concentrate even more at the area of interest. So by comparing all these different strategies to combine the two, we realized that the simultaneous RH refinement is the more suitable to do. And another ingredient in this process is where you do your what you use to solve your Monge-Apour equation. What basis you use to solve your relocation problem. Since so and then with these examples, we actually wanted to keep the computational cost low. So we always solve the initial Monge-Apour equation on a tensor product basis. We don't use the adaptive basis, the adaptive H refinement to relocate the nodes. When doing that, there's one advantage is that we can use fast diagonalization. So it means we can exploit the tensor product structure of the tensor product splines in order to reduce the computation time. So it's a known technique when you have a tensor product grid that you can actually solve this equation on the square with much less computation time than if you would use the full solver. Like here we compare with the conjugate gradient solver that uses n squared number of degrees of freedom, and fast diagonalization would reduce the problem to a number of n times n smaller problems. Anyways, long story short, the best thing is we obtain good results with fast diagonalization and conjugate gradient, but with respect to CPU time, the best is to use fast diagonalization for this step. And that's what you get as some resulting meshes. That's pure H refinement. That's one R and then two H refinements, and that's two successive RH cycles. Well, you don't see much of a difference in these meshes, but it's because I cannot really draw very fine meshes because you cannot see them anymore. But in general, what we have observed is that the RH, the SUM approach, or the simultaneous RH refinement, is what works the best because it at every step it can relocate and improve the mesh closer to the features of the density. So you see the density here dictates that we should concentrate the mesh along these swirl lines. Okay, and again, this is some meshes with simultaneous refinement. On the top, you have pure H refinement, and on the bottom, you have H refinement, but it is enriched with R refinement. In practice, what do we see? In this R refinement, what is important is that the mesh can be aligned to your features. No matter how far you might do H refinement here, the parameterization cannot rotate, will not rotate, is fixed. So your elements will not rotate and they will not be aligned to your feature. Whereas here, when you allow to relocate the nodes, you see that there is some rotation happening and the alignment is much better. So that's why we believe that the combination of the two can bring the best of both worlds. So then we put everything together. One more ingredient is that we need to actually generate this monitoring function. And when you have an a posteriori error estimator, usually you have an error value for each element. So you know that the error is that or that in every element, but that's a discontinuous function. These are just sub-values. And the first thing we want to do is to actually generate a smooth monitoring function, because we need such a function for solving the optimal transport problem. So what we do is that we project these values on a grid. We project it using a projection operator, and we obtain a spline function that we can use in the sequence, a smooth. So we smooth out the error, and this error, as you see here, is the PD operator minus the right-hand side, so it's the residual error, okay, on every element. Q is every element of our mesh. There you have another example. On the left, just pure edge refinement, and on the right, on this sphere, you also have mesh alignment together, RH adaptive refinement. And on that one, you can see that if you compare with uniform refinement, which is the blue, you compare with pure edge refinement with different refinement thresholds. And if you do just R refinement, which you would do on a tensor product grid, all of these become not as efficient as if you would do what we propose, the combined RH refinement. Here we could not do another step actually, because to do another global step we would have to refine globally one more time the tensor product basis, and this would make the number of degrees of freedom to explode. Whereas here you see that aligning the mesh with R and locally refined with H gives the best results. And with respect to H1 error, the picture is the same. Okay, and yes, one last example. Here we solve a advection diffusion equation. Here is with just locally refined THP splines. And you see that we get a nice solution, but in these sharp layers, you see that even though we put a lot of degrees of freedom, we don't arrive to completely eliminate this effect of the transition. Oops. But if we do an R refinement step, then we better align the mesh, and the sharp layers become much sharper with the same number of degrees of freedom. So we are much more satisfied with this than with the original solution. And another one is we applied this with to the elasticity benchmark on this quarter annulus. Again, the RH is the more efficient to do. And yes, you can see that if it was a pure H refinement, then you would get this kind of mesh. But if you do RH refinement, the original mesh concentrates close to the high stress areas, which is this part here. And then the H refinement refines in a different way, so to say. Okay, so to draw some conclusions, we tested this technology of RH refinement by combining node relocation and local refinement in order to get the best traits of both worlds. I would say the best trait of local H refinement is that you can locally refine the mesh at will where you want it. But the extra trait that is very interesting in relocation refinement is that you can align. You can align and you can reparameterize so that you capture much better features on your solution. And yes, another thing that we're investigating is how to how to make this technology compatible with the rest of CADs, so to say, because as you might have noticed, when we apply this RH refinement or this R refinement in general, our final object, our geometry, is not anymore a spline, but it's a composition of two splines. So in that case, this is not directly compatible with CAD systems, and we would have to find a good way to project back to the spline space or to export to something which is compatible. And so with this, I'd like to thank you for your attention.
Yes, very easy. Very easy. Thank you, Alex.
Thank you.
So, always first are
Not always. So our method of choice is to do successive RH at every cycle. Yes, first R and then H. Yeah. Mhm. We can do both. The reason why we do first R is because we want to stay with the tensor product basis as much as possible. And yes, first we only have the tensor product basis, and solving there is efficient. So that's why first we do the R.
and then we do double part of these, then we go to these slides.
We still use an underlying tensor product mesh because it's more efficient. Mm.
Yes. This makes also small civilization over. What's the main problem? Significantly consider move the mesh. What is the trigger?
Yeah,
Of course, it's very amazing.
I see.
It's
Yeah. Yeah. Okay. So for getting the first of all, it is a method that is known in finite elements mostly. Recently, in isogeometric analysis, pure AR refinement. I guess there is some extra layers. There is this density function that you need to approximate. There is this extra system to solve. Here we alleviate that because we go to the unit square. We solve the equation from unit square to the unit square. You can imagine in an unstructured mesh, you cannot play this trick. So you have to solve another PD before solving your PD to get the mesh. And what else? Maybe also, of course, there are always problems with bijection. Maybe in some cases you don't get bijectivity. Yeah, maybe there are all these things to consider. So to say, it's an advanced remeshing method. So it comes with all the problems of that, for sure. Thank you.
These topic is also very relevant. I will in part depends on
Times next section.
Yeah.
Yeah.
Yeah, yeah. We can do together.
Yes, please.
This is being installed. It's saving.
Hello everyone, I'm Jin Yizhao, a PhD student from Dalian University of Technology in China. My report is Extended or Adaptive Isogeometric Analysis for Weak Discontinuous Problems. The co-operators on this paper are Ye Ji, Matthias Müller, and Zhu Chungang. I will introduce it from the following four aspects. First, I want to introduce what the weak discontinuous problems is. Weak discontinuity problems are a type of physical problem where the solution is continuous, but the derivative of the solution is not. There are many reasons for this kind of discontinuity. Compositions, layered structures, pore source, anyway interfaces are frequent in engineering and biomedicine. For example, in the figure, the stone wrapper in concrete on the left and the tooth and the surrounding bones tissues on the right are common inclusion problems. This kind of discontinuity will affect the accuracy unless the discretization is adapted to the interface geometry. This is the interface boundary condition. To deal with the discontinuous here, a lot of methods have been proposed. Edge refinement, accurate but cumbersome for complex geometry. Extended finite element method, capture the jump but as degree of freedom. Isogeometric analysis method, exact geometry, high smoothness, but that smoothness is run across a kink. Are adaptive alone in isogeometric analysis method. Relocates points, provides guide, but can't reproduce the derivative jump. In isogeometric analysis, splines used to represent the physical domain are also used to construct the solution in the computational domain. However, only the control points located on the boundary affect whether the spline combination can accurately represent the physical domain. Therefore, we can remove mesh quality by moving the coordinates of internal control points. This approach doesn't change the mesh topology or add extra degree of freedom, and it allows the mesh to better adapt to key areas of the problem. Extended isogeometric analysis is a method which combines the geometric advantage of isogeometric analysis with the enrichment strategy of extended finite element method. But geometric resolution still misaligned with interfaces. So we proposed extended or adaptive isogeometric analysis. It's worth maintaining that our adaptive method account for less than 1% of the total computation time. The next part is our method and algorithms. Our method compiling enrichment with control points relocation. Enrichment provides the approximation space needed to represent the current jump. Our adaptive redistribute the existing resolution towards the interface. Finally, the accuracy improved by more than 16%, and the extra time it took was less than 1%. I want to first introduce some knowledge related to the extended isogeometric analysis. It's a strong form for linear elasticity with weak discontinuous. U represent the unknown displacement. Sigma is the strength tensor and B is the body force. This is the interface boundary conditions. These conditions indicate the discontinuity of the displacement garden at the interface. Simplified to the weak form based on the principle of minimal potential energy, and on this basis, use extended isogeometric methods. Based on the partition of unit enrichment paragraphy, the extended isogeometric method adds enrichment functions to the interface-related parts to capture the special changes near the material interface. Only control points whose support interfaces are enriched cite n faces. The enrichment function phi is contributed from the level set functions, which is used to distribute the position of the material interface. When it equals to 0, its correspondence to the interface, where the materials meet in the physical regions. This is the mixture assemble process, and adding the extended part can fix the discontinuous of this kind of problem. When solving these problems, there are two types of the elements, standard elements and cut elements. For standard elements, a Gaussian integration with P71 multiplying Q71 points is used. For cut elements, if we still directly use standard Gaussian integration, the integration points may fall into different material regions at the same time, which would reduce the solution accuracy. So a stage of subdividing into smaller triangles is used, with 30 integration points for each subdividing triangle. The picture below shows from the integration points are distributed under the integration strategy. In the zoomed-in image in the right, the black triangles represent the sub-element divisions, and the red dots are the integration points. To check how the optimization method improves the accuracy of solving the problem, we use related energy error as the measurement standard. According to the error estimation method proposed by ThinkWiki and others, the small strange field variable S is used instead of the real strange field epsilon to calculate the error. The whole computation process can be divided into three parts. First, in the physical space, we based on the KS allocation to use level set functions, building a function. This function's value represents the proportional distribution of geometric redistributions weights in the physical domain. Then we use this function to build a Gaussian type multiple function. The multiple function is used to update the control points in the parametric space. Finally, the physical equations are solved based on the updated control points. This process have no knock insertion, no degree division, and the typology preserved. Then I want to introduce the specific process of constructing the multiple function. The function constructed based on the KS allocation is as follows. Here, phi kx is the level set functions. Use phi x to construct the monitor function in the following format. Based on this function, we then constructed an electric obtainer to solve the new control points. The method works for any number of methods. The multiple function reached its maximal value, rho max equal rho 0 or multiplying alpha at the interface, and smoothly decreases to the background level rho 0 as the distance from the interface increases. So alpha rate rho 0 determines the magnitude of function's variations, while delta controls the distance of the multiple function's influence. Based on our method, we construct the monitor functions and move the guide on the letters SPM. Figures A to C shows the numerical distribution of the level set functions for 3. Figure D shows the maternal functions constructed using the KS allocation method. Figure E shows the quality function, and the final grid moment effect is shown in Figure F. We use a PDE-based R-adaptive parametrization method. By solving the equation, we get new control points. This equation can be understood as the Euler-Lagrange equation of geometric functional, which rearranges the distribution of control points according to the numerical distribution turns to the maternal function. To keep in the geometric distribution, the control points on the boundary remains unchanged, and it can be eventually by simplified to solving the following equation. The whole process is a positive, definite linear solve and doesn't depend on the initial solution. Also, the time span increases with the number of control points. The overall obtained process can still take up less than 1%. This part is the benchmarks and results. This is an example of a circular air with two materials. Figure A, C, D are the exact solution of displacement, the numerical solution, and the absolute error distribution. Figure B is the result of our adaptive parametrization. It can be seen that the degree of freedom tend to contribute at the boundaries. The left image shows the relative errors calculated and compared on the same set of degree of freedom for four methods: XFEM, XFEM combined with R adaptive, XIGA, and XIGA combined with R adaptive. It can be seen that our adaptive optimization can constantly improve the calculation accuracy, and the degree of freedom increase, the operation count becomes even more noticeable. The right image shows a comprehension of computational costs, and the time used for operation always counts for less than 1% of the total time. This is the example of four calcular interfaces. From this, we can see that the method can also improve accuracy when there are multiplying interfaces. This is examples for three calculator interfaces. Even though the interfaces are closely packed, our method can still optimize their eventually. This is an example of a heart-shaped interface. The type of the heart is a special point that needs excitable attention. As can be seen from the figure below, the error is eventually introduced while still ensuring computation efficiency. Finally is the conclusion and the outlook. First, we proposed a copter enrichment and adaptive strategy within the isogeometric analysis framework is developed for problems with weak discontinuous. Secondly, a monitor function was constructed when greatly reduced errors while taking little time. Finally, various numerical examples show the effectiveness of this method. For future work, we plan to extend it to 3D problems and more example problems. Using this method for problems with strong discontinuous. Thinking about setting up a more automated optimization strategy. Thank you everyone for listening. Here is our method. Feel free to contact us if you have any questions.
Maybe I will ask what okay, I'm not really expert in this field, but I will come explicitly all those injective constraints in your method, which means that the measurement of with each other and it be controlled in your method.
Can you speak again?
Yeah. So because the control point is being modified, right?
Yeah.
And you guarantee that the mesh will not fall in with each other after the update.
Yeah, we can move them again for another.
So is this considered by any objectives?
Yeah.
Yes. Yes. Yeah, it's a guaranteed experience. It's basically it's easy for because we small it's common and according to the law theory, it's guaranteed on the 20 but usually okay. Thank you. See, bye bye. let's ask another one. Sorry. So for the extension of 3D, how challenging will
Maybe we do it now, and we will take actual later, and maybe the extended part may be different, and the adaptive to 3D is, yeah, naturally.
Okay, so maybe we can make that. Great. So if no more question, I thank the speaker again. I thank the